We think we have a pretty good handle on our universe. Trillions of galaxies, each with billions of stars, all expanding from a single point in the Big Bang. But what if this entire, vast cosmos is nothing more than a single atom in a reality so immense we can't even begin to imagine it? It turns out, our most basic assumption about the universe, that there's nothing outside of it, might be completely wrong. And scientists are starting to find some very strange reasons to believe that what we see is not all there is. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Let's start with a little thought experiment. Imagine a colony of ants living on a vast, flat sheet of paper. To them, their world is a simple, two-dimensional expanse. They can move forward, backward, left, and right. That's it. Their entire reality is confined to this plane, with no concept of up or down. If you, a three-dimensional being, were to gently lower a leaf onto their path, it would look like it materialized from nowhere. If you lifted one of the ants, it would simply vanish from their universe. From their perspective, their flat world is all that exists. It's a self-contained reality. Why would they ever question it? Their entire evolutionary history has been shaped by the rules of their 2D existence. Now, let's scale that up. We humans live and see the world in three spatial dimensions: length, width, and height, plus the steady forward march of time. Our brains are hardwired for this 3D reality. Every tool we build, from a simple hammer to the James Webb Space Telescope, is designed to interact with this world. Our survival never depended on thinking about a fourth spatial dimension. It depended on judging the distance to a predator or the path of a thrown spear. So, when we look out into the cosmos, we see a universe that's about 93 billion light-years across. We see galaxies and clusters stretching in every direction. And, just like the ants, we instinctively assume this is it. This is the whole shebang. The ultimate container. This isn't just a casual thought, it's a quiet rule that underpins almost all of modern science. We call it the idea of a self-contained cosmos, the belief that there's nothing bigger, nothing outside the universe. It's a bit like living in a house your entire life and, after exploring every room, concluding that your house is the entire planet. You've never seen a door leading outside, so you assume there is no outside. This assumption simplifies things enormously. It gives us a closed system to study, a cosmic laboratory with defined boundaries. But what if this assumption, as logical as it feels, is just fundamentally wrong? What if we're the ants, totally oblivious to the dimensions just beyond our senses? The story of our universe might only be the first chapter of a much, much larger book. And for the first time, we're finding pages from that book we never knew existed. The Cosmological Principle. A universe of cosmic vanilla ice cream. To really get why challenging this idea is so radical, you first have to appreciate just how well it has worked. Our model of a self-contained universe is built on an idea so fundamental, it's often called the backbone of modern cosmology. The Cosmological Principle. In simple terms, the Cosmological Principle says two things about the universe on the grandest scales. First, it's homogeneous, meaning that no matter where you are, it looks pretty much the same. There are no special spots. The density of galaxies in 1 billion light-year wide cube of space is, on average, the same as any other. Second, it's isotropic, meaning it looks the same in every direction you look. There's no cosmic, North Star, or special axis for the cosmos. Think of it like a giant tub of cosmic vanilla ice cream. A scoop from the top left corner is going to be the same vanilla as a scoop from the bottom right. And if you look at the tub from any angle, it just looks like a smooth, uniform sea of vanilla. No big chocolate swirls, no massive chunks of fruit. On the largest of scales, the universe is smooth and predictable. This isn't just a nice thought, it's a mathematical lifesaver. When Albert Einstein first tried to apply his theory of general relativity to the whole universe, the equations were a nightmare. But by assuming the universe was smooth and uniform, the math simplified dramatically. It allowed physicists to treat the entire cosmos as a single, evolving thing. And out of this simplified model, known as the FLRW metric, pretty much all of modern cosmology was born. The predictions were astounding. The equations said the universe had to be either expanding or contracting. This was years before Edwin Hubble actually saw that distant galaxies were rushing away from us. The model also predicted the cosmic microwave background, CMB, the faint, thermal afterglow of the Big Bang from when the universe was just 380,000 years old. When the CMB was finally discovered in 1965, it was almost perfectly uniform, just like the principle suggested. The temperature of this ancient light is the same across the whole sky, with tiny fluctuations of only about 1 part in 100,000. This amazing smoothness is considered one of the strongest proofs of our standard model of cosmology. On top of that, the model accurately predicts the amounts of the lightest elements hydrogen, helium, and lithium that were created in the first few minutes after the Big Bang. The amounts we see today match the predictions with incredible accuracy. So, for decades, the cosmological principle has been a huge success. It works. It gave us a framework that explains the universe's expansion, its afterglow, and its chemical makeup. But as our telescopes have gotten more powerful, peering deeper into the dark, we've started to see things that don't quite fit the picture of smooth, uniform vanilla ice cream. We're finding lumps. And some of them are colossally, impossibly big. The cracks in the foundation. Mega structures that shouldn't exist. For a long time, the cosmological principle was king. Sure, the universe wasn't perfectly smooth. Gravity pulls matter into stars, galaxies, and clusters. Those are the expected lumps. But our models predicted a limit. Cosmologists figured that gravity just wouldn't have had enough time since the Big Bang to build structures bigger than about 1.2 to 1.6 billion light-years across. Anything bigger would be a major anomaly, a direct challenge to the idea that the universe is the same everywhere. And then, we started finding them. In 2013, astronomers studying gamma-ray bursts noticed a shocking concentration of them in a distant patch of the sky. The collection was so huge it was named the Hercules Corona Borealis Great Wall. Current estimates put it at up to 10 billion light-years across. That's more than a tenth of the diameter of the entire observable universe. A structure so big that light would take 10 billion years to cross it. The existence of a wall of galaxies this vast is a serious problem for the Standard Model. Now, its existence is still debated. Some scientists think it might just be a statistical illusion, a chance alignment of smaller clusters. But the Great Wall isn't the only one. In 2021, a team led by cosmologist Alexia Lopez discovered another. The giant arc a breathtaking crescent of galaxies stretching 3 billion light-years. It's so big that if you could see it at night, it would be as wide as 20 full moons. The odds of something like this forming by chance are incredibly low. Then, things got even weirder. In early 2024, Lopez and her team announced another enormous structure, seemingly in the same cosmic neighborhood. The Big Ring. It's a colossal ring of galaxies about 1.3 billion light-years in diameter. What's really mind-boggling is how close it is to the giant arc. Lopez herself said, "From current cosmological theories we didn't think structures on this scale were possible. We could expect maybe one exceedingly large structure in all our observable universe. Yet, the Big Ring and the giant arc are two huge structures and are even cosmological neighbors. Like the Great Wall, these discoveries are controversial. Some astrophysicists argue we're just seeing patterns in random data, not real, physically connected superstructures. But the growing list of these cosmic giants is putting the cosmological principle under serious pressure. They're lumps in the ice cream that are just too big to ignore. This leaves us with a choice. Do we try to stretch our existing theories to their breaking point? Or do we dare to ask a more radical question? What if the principle itself is wrong? What if these structures aren't just flukes, but signposts pointing to a deeper, hidden reality? The whisper of a fifth dimension. The idea of more than 3 spatial dimensions isn't new. It's been floating around theoretical physics for over a century. And it all started with an attempt to unite the forces of nature. Back in the early 20th century, physics had two main theories: Einstein's general relativity for gravity, and Maxwell's theory for electromagnetism. They both worked perfectly, but they were separate. In 1921, a little-known mathematician named Theodor Kaluza sent a letter to Einstein with a wild idea. Kaluza suggested that if the universe had not 3, but 4 spatial dimensions, something magical happened. He wrote out Einstein's equations in 5 dimensions. 4 of space, 1 of time, and when he crunched them back down to our world, he got general relativity back. But he also got Maxwell's equations for electromagnetism, which popped out of the math for free. In this model, electromagnetism, the force that gives us light, was just a ripple in this unseen 5th dimension. As physicist Michio Kaku puts it, the extra dimension provided enough room for both gravity and light. But if this 5th dimension exists, where is it? A few years later, a physicist named Oscar Klein came up with a brilliant answer. He proposed that the 5th dimension isn't huge like ours. Instead, it's curled up into a tiny, microscopic circle, too small for us to ever see or interact with. Imagine a garden hose. From far away, it looks like a one-dimensional line. But up close, you see it has a second dimension. The circle you can go around. Klein suggested that every single point in our 3D space has one of these tiny, curled-up dimensions attached to it. This Kaluza-Klein theory was a stunning achievement, but it was incomplete and had its problems. The idea was mostly set aside for decades. But the seed was planted. The concept that our reality might just be a slice of a much bigger, higher-dimensional space was too powerful to forget. It just needed a new theory, one that would need more dimensions than ever before. Weaving the cosmos with strings. By the mid-20th century, physicists had discovered 2 new forces: the strong and weak nuclear forces. The dream was now to unite all 4 forces: gravity, electromagnetism, and the 2 nuclear forces under the strange rules of quantum mechanics. This is the challenge that gave birth to string theory. The central idea of string theory is that the fundamental building blocks of the universe aren't particles, but tiny, one-dimensional vibrating strings of energy. Like a violin string, different vibrations produce different notes. In string theory, the different vibrational patterns of these tiny strings show up as all the different particles and forces we see. One vibration looks like an electron, another looks like a photon, and another looks like a graviton, the particle of gravity. In this view, the whole universe is just a grand cosmic symphony. It's an incredibly elegant idea. But there was a catch. The math of string theory just didn't work in 3 spatial dimensions. It was full of paradoxes unless it was formulated in a universe with many more. The best versions of the theory required a total of 10 or 11 spacetime dimensions, or 3, 1 for time, and 6 or 7 extra spatial dimensions curled up and hidden from view. And once again, the answer was that they are compactified, or curled up, on a scale so small we could never see them. But instead of a simple circle, string theory suggested these dimensions could be curled up into incredibly complex, six-dimensional shapes called Calabi-Yau manifolds. The precise geometry of these hidden shapes would determine the laws of physics in our universe, things like the mass of an electron or the strength of gravity. It's a mind-bending idea. It suggests the answer to why our universe is the way it is lies not in the world we see, but in the twisted geometry of a space hidden within every point of our own. For years, string theory has been criticized as untestable. But it also offers potential solutions to some of the biggest puzzles in physics, puzzles that might be pointing us toward these hidden realms. Solving cosmic puzzles. Weak gravity and fading dark energy. Extra dimensions aren't just a mathematical curiosity. They could also solve some of physics' most stubborn puzzles. Two of the biggest are the weird weakness of gravity and the deep mystery of dark energy. First, gravity. Of the four fundamental forces, gravity is by far the weakest. The magnetic force holding a magnet to your fridge easily overpowers the gravitational pull of the entire Earth. The electrical repulsion between two protons is about 10 to the power of 36 times stronger than their gravitational attraction. Why is gravity so unnaturally weak? This is called the hierarchy problem. Higher dimensional theories offer a fascinating answer. They suggest that while the other forces are stuck to our three-dimensional universe, or brane, gravity is different. Gravity is the force of spacetime itself, so it can leak out into all the extra dimensions. Imagine our universe is the 2D surface of a pond. When you drop a pebble, the ripples, like electromagnetism, spread out only on the surface. But the sound of the splash, gravity, travels out in all three dimensions. Because gravity's influence is spread thin across these extra dimensions, it seems much weaker to us, who are trapped on the surface. The second puzzle is dark energy. In 1998, astronomers discovered the expansion of the universe is accelerating. Some mysterious force, which we call dark energy, is pushing everything apart. But some recent and highly speculative data from instruments like DAISY has hinted that dark energy might not be constant. One new theory from early 2026 even suggests that if dark energy is fading, the cosmic acceleration could be temporary. The universe's expansion might eventually stop, and reverse into a big crunch, about 20 billion years from now. Now, I have to be clear. This is a brand new, very speculative idea, and other analyses of the same data support a constant dark energy. But the very possibility that dark energy can change opens the door to higher dimensional explanations. In some string theory models, the behavior of dark energy is tied to the slow shifting of the extra dimensions. The strange behavior of dark energy could be the first whisper we're hearing from a higher dimensional reality. The dark matter enigma. Beyond dark energy, there's another, dark, mystery, dark matter. Astronomers have seen that galaxies are spinning way too fast. Based on the stars and gas we can see, the outer stars should be flung off into space, like kids flying off a merry-go-round. The only way they hold together is if they're embedded in a huge, invisible halo of some other kind of matter that has gravity but doesn't interact with light. We call it dark matter, and we think it outweighs all normal matter by more than 5 to 1. But we have no idea what it is. This has led physicists to consider more exotic ideas, many of them again rooted in extra dimensions. One idea is that dark matter isn't a new particle at all, but the gravitational shadow of matter in a parallel universe or a nearby brane. Another possibility comes from the old Kaluza-Klein theory. If there are extra, curled-up dimensions, our normal particles should have heavier echoes, called Kaluza-Klein or KK particles. A KK particle is just like its normal twin, but it has extra energy from moving around the hidden dimension, making it appear much heavier to us. The lightest of these KK particles could be stable, heavy, and neutral, a perfect candidate for dark matter. These theories show how extra dimensions could provide a framework for a hidden, parallel reality that is gravitationally shaping our own. The missing mass of the universe might not be missing at all, it might just be in a place we can't look, its presence revealed only by the shadow it casts on our world. A new origin story. The Big Bang on a brane. Maybe the most profound implication of higher dimensional physics is how it could rewrite the story of the Big Bang. In the Standard Model, the Big Bang is the beginning of everything, exploding from an infinitely dense point called a singularity. But that picture doesn't explain what caused it, or what came before. It's a point where our laws of physics just break down. Brane cosmology offers a radical new origin story. In this model, our entire universe is a brane, a membrane floating in a higher dimensional space called the bulk. Think of our universe as one slice of bread in an infinite loaf. There could be other branes, other parallel universes, floating right alongside ours. In this picture, the Big Bang wasn't the beginning of time. It was just an event that happened in this larger space. One popular version, the ekpyrotic model, proposes that the Big Bang was caused by the collision of two parallel branes. Imagine two vast, universe-sized membranes moving through the bulk, drawing closer, and finally, colliding. The cataclysmic energy from that collision would heat the branes to incredible temperatures and create a hot, dense soup of particles which would look exactly like the Big Bang to anyone living on one of the branes. The impact's energy would become the matter and energy of our universe, and the rebound would drive cosmic expansion. This idea neatly gets rid of the singularity problem. The universe was never a single point. And it answers the "what came before?" question. Before the bang, there were two branes, moving through the bulk. This could even be a cycle, with the branes colliding and rebounding over and over, endlessly rebirthing the universes. There's no direct proof for this yet. And while it's tempting to see giant structures like the giant arc as evidence, that's an overstatement. They're anomalies that make these wild ideas more attractive to theorists, but they aren't proof. Still, a brane collision might produce a unique type of gravitational wave that we could one day detect. If we ever found that, it would completely change our cosmic narrative. The existential implications. Beyond the cosmic horizon. We're standing at a precipice, staring into an abyss of possibilities. We started by assuming the universe we see is all there is. We've journeyed through the cracks in that assumption, from impossible structures in the sky to the theoretical whispers of hidden dimensions. Now we have to ask, so what? What does it mean for us if we're living inside a higher dimensional structure? On one level, it's incredibly humbling. All of human history, every star, every galaxy we can see, could be just one tiny piece of a reality vastly more complex than we ever imagined. Our cosmic horizon might not be the edge of existence, but just the edge of our perception. The image of Russian nesting dolls comes to mind. We thought our universe was the biggest, outermost doll. Now we face the possibility that our doll is just one of many, nested inside another, and another. It redefines our place from being the inhabitants of the universe to being inhabitants of *a universe. That can be a little unsettling, right? It challenges our sense of importance. But it can also be a source of profound wonder. It means the mysteries don't end at the edge of our vision. The ultimate laws of nature might be written in the language of a higher dimensional geometry. This perspective gives the search for knowledge a new purpose. When we build bigger particle accelerators or more sensitive telescopes, we aren't just filling in a map. We're searching for the first real clues of a world beyond our own. The anomalies we find, the megastructures, the weird behavior of dark energy, are no longer just problems. They're potential windows, cracks in the veil through which we might glimpse the true nature of reality. Ultimately, this is a story about the boundaries of what we know and the courage to question what we think we know. For millennia, we've looked at the stars and tried to understand our place in the cosmos. We might be on the verge of discovering that our place is far stranger and far more magnificent than we ever dared to dream. So, are we living inside a higher dimensional structure? We don't have the final answer yet. What we do know is that the comfortable, self-contained picture of our universe is starting to show its age. We're finding colossal structures that defy our models, and our deepest theories of physics keep pointing toward more dimensions than we can see. These ideas, from strings and branes to a big bang caused by a cosmic collision, are still on the frontiers of science. They're speculative, not yet proven. But they are serious, mathematical frameworks built to solve real problems. They represent a fundamental shift in how we think about reality itself. We might be like those ants on the paper, unaware of the vast third dimension all around us. But unlike the ants, we can reason, imagine, and follow the clues. We're beginning to see the shadows of things lowered into our world. The journey to understand what they are will be one of the greatest adventures in human history. The sky is no longer the limit. It might just be the floor of an infinitely grander stage. What do you think? Are these mega structures proof that our cosmic theories are broken? Or are they the first hints of a reality beyond our own? Let us know your thoughts in the comments below. The invisible directions hiding all around you. Go ahead, look around. You can move forwards and backwards, left and right, up and down. These three directions define your entire world. They give length, width, and depth to everything you've ever seen, touched, or known. It feels complete, right? Like that's the whole story. But what if it isn't? What if I told you that science has a very good reason to think there are other directions hidden all around you? That they exist at every single point in space, but are curled up so impossibly tight that they're invisible to us, and even to our most powerful instruments. This isn't some wild philosophical guess. The idea of hidden dimensions comes straight from the heart of theoretical physics, and it might just be the answer to the deepest questions we have about reality. And finding these hidden paths isn't just a neat party trick. It could prove our universe is far stranger and more complex than we ever imagined. It might just be the key to everything. So, how can a direction be hidden? And why do some of the smartest people on Earth think they have to exist? To answer that, we need to start big. Really big. We have to start with a cosmic war raging at the heart of physics. The cosmic conflict. A universe divided. At the start of the 20th century, physics was having an identity crisis. We had two incredible new theories that were amazing at describing the universe. The problem was, they described two totally different universes. On one side, you've got Einstein's masterpiece, general relativity. Think of it as the poetry of the cosmos, describing the universe on the grandest scales. It says space-time isn't an empty stage, but a stretchy fabric. A massive object like a planet doesn't just sit in space, it bends it, like a bowling ball on a trampoline. What we call gravity is just us, following the curves in space-time. It's a beautiful theory that governs dancing planets, dying stars, and the birth of the universe itself. General relativity is the king of the really, really big. But then, you have the other side. The world of the impossibly small. This is the turf of quantum mechanics. And if general relativity is a graceful ballet, quantum mechanics is a chaotic, unpredictable rave. See, down at the subatomic level, things get weird. Particles don't really have a single location. They exist in a fuzzy cloud of probability, only snapping to one spot when we look at them. This theory governs the particle zoo. The quarks, electrons, and all the other tiny bits that make up you and everything around you. It's the undisputed, and deeply strange, queen of the microcosm. For a century, these two theories have been the pillars of physics. Both are spectacularly successful. Your GPS works because of general relativity. The device you're watching this on works because of quantum mechanics. They are both, without a doubt, correct. And they absolutely, fundamentally, cannot stand each other. The fight breaks out when you try to describe something that's both incredibly heavy and incredibly tiny. Think about the heart of a black hole, a singularity, or the very first moment of the Big Bang. To understand those, you need both theories. But when you try to use them together, the math just breaks. The equations spit out nonsense, like infinity, telling us our two best descriptions of reality just don't work together. This isn't just a small disagreement. It's the biggest, deepest hole in all of modern science. A cosmic conflict that screams at us that our understanding is incomplete. There has to be a deeper theory, a theory of everything, that can unite them. And it's in the hunt for this unified theory that a weird, century-old idea made a comeback. The idea of a hidden, fifth dimension. The first glimmer, a fifth dimension. Our story starts not with a giant particle accelerator, but with a letter. It's 1919. General relativity is brand new and has just passed its first big test. The world of physics is buzzing. A German mathematician named Theodor Kaluza decides to try something bold. He's fascinated by Einstein's equations, which describe gravity in 4 dimensions, 3 of space, 1 of time. So Kaluza asks a simple question. What if there were 5? He took Einstein's famous equations and just rewrote them for a universe with 1 extra direction of space. And when he worked through the math, something truly magical happened. The equations naturally split into 2 parts. One part was, of course, Einstein's original theory of gravity. But the other part was something else he recognized instantly. Maxwell's equations for electromagnetism, the force behind light and electricity. Let that sink in for a second. This was astonishing. Just by adding 1 more direction, Kaluza found that the 2 forces known at the time, gravity and electromagnetism, popped out of a single theory. It suggested that gravity is a ripple in the dimensions we know, while electromagnetism could be a ripple in this new, 5th dimension. Light itself might just be a vibration traveling down a hidden road that's woven into every point in space. Kaluza sent his work to Einstein, who was blown away, saying the idea had enormous appeal. But there was one glaring problem. Where is it? We can't see a 5th dimension. A few years later, in 1926, a physicist named Oscar Klein added the missing piece. He brought in the new, weird ideas from quantum mechanics and proposed a brilliant solution. The 5th dimension is real, it's just not big and stretchy like ours. It's curled up into a tiny circle. And this brings us to probably the most famous analogy in all of physics: the garden hose. From far away, a garden hose looks like a one-dimensional line. An ant on it can only move forward or backward. But if you get close, you see there's a second dimension you missed. The little circle the ant can walk around. Klein proposed our universe is like that. At every single point in space, there's a tiny loop of a 5th dimension, curled up so mind-bogglingly small we're talking the Planck length, about 10 to the minus 35 meters, that we could never see it. You could travel around this loop trillions of times and never even know you were moving. This Kaluza-Klein theory was an amazing achievement. It united forces and gave a great reason for why we don't see the extra dimension. But the theory wasn't perfect. Soon, 2 new forces were discovered: the strong and weak nuclear forces, and the theory had no room for them. But the idea, as beautiful as it was, faded away for a while. It never really died, though. It was just waiting in the wings for a new, even bolder theory to bring it back. A theory that wouldn't just add 1 extra dimension, but 6. A theory made not of points, but of strings. The symphony of strings. Flash forward to the 1970s, and physics was in trouble again. Our main theory, the Standard Model of particle physics, was a huge success. It described all the known particles and forces, except gravity, perfectly. But it was also, well, a bit of a mess. It had dozens of particles and around 20 numbers that had to be measured and plugged in by hand. It told us how the universe worked, but not why. Why these particles? Why these numbers? Physicists were searching for a deeper idea. The answer they found was one of the most radical ideas in the history of science. What if the most fundamental thing in the universe isn't a tiny point-like particle, but a tiny, vibrating, one-dimensional filament of energy? A string. This is the core idea of string theory. And it changes everything. Think about a violin string. By vibrating it differently, you can make a bunch of different notes. The big idea of string theory is that the universe works the exact same way. Every particle we see, an electron, a photon, a quark, is just a different note being played by these tiny, vibrating strings. The entire particle zoo is just a cosmic symphony. This is the mind-blowing part of string theory. It unites everything. Not just the forces, but matter and force. Everything you are, everything you see, is all made of the same stuff. But, as physicists dug into the math, they hit a familiar roadblock. But this time, it was on steroids. For the math of string theory to work without falling apart, the universe must have more dimensions. And not just one more. The leading version of the theory requires a mind-boggling 10 dimensions in total. 9 of space and 1 of time. And why 10? That number isn't just pulled out of a hat. In a 10-dimensional universe, all the mathematical problems that would normally break the theory just cancel out. These extra dimensions aren't an optional extra, they're a mathematical requirement. Without them, the theory falls apart. This brought back Klein's idea of curled-up dimensions with a vengeance. If string theory is right, then at every point in space, there are 6 other directions, all hidden from us. And as the theory grew, it got even weirder. It turned out there were 5 different versions of string theory. Then, in the 1990s, physicists proposed they were all just different views of a single, even bigger, 11-dimensional theory called M-theory, where the M famously stands for mystery, magic, or mother, depending on who you ask. So that's where we are now. Our most promising theory of everything says that our vast universe is just a small slice of the whole picture. That we live in a world with 6 or 7 invisible dimensions. But if they exist, what are they for? Well, it turns out they're not just sitting there. They're actively shaping our reality. Hiding a universe. The geometry of the unseen. Okay, so if string theory is right, we have 6 extra dimensions curled up everywhere. But how are they curled up? It's not a simple circle anymore. With 6 dimensions, the ways they can be folded get incredibly complex and incredibly important. These shapes have to follow Einstein's laws, and mathematicians had already been studying a family of fantastically complex, 6-dimensional shapes that fit the bill perfectly. They're called Calabi-Yau manifolds. Now, trying to actually picture one of these is, well, it's impossible for our 3D brains. Think of it like this. You can take a 2D piece of paper and roll it into a cylinder or fold it into a complex origami crane. Now imagine doing that with 6 dimensions, with twists and holes all interconnected in bizarre ways. In string theory, the exact shape of this hidden space is everything. It's the master blueprint for our universe. Why? Because the geometry of this hidden space decides how the strings are allowed to vibrate. Remember the violin? The notes it can play depend on its shape and the tension of its strings. It's the same here. The possible vibrations of a string, which means the types of particles that can exist, are determined by the shape of the Calabi-Yau manifold. For example, the number of holes in the shape is thought to determine the number of different families of particles. We know of 3. String theory suggests that's because the hidden dimensions are folded into a shape with 3 holes. The size and shape of those holes then determine the mass and charge of the particles. Think about what that means. It's a breathtaking claim. The deepest questions in physics: why does an electron have the mass it does? Why is gravity so weak? Might just be questions of geometry. The fundamental rules of our universe aren't random. They're echoes of the geometry of this hidden, six-dimensional world. But this amazing promise comes with an equally amazing problem, one so big it's just called the landscape. It turns out there isn't just one Calabi-Yau shape that works. There could be an astronomical number of them. The current estimate? There could be at least 10 to the 500th power. That's a 1 with 500 zeros after it possible shapes for these hidden dimensions. Each of those shapes would create a universe with its own unique laws of physics. So which one is ours? And why this one? Does this mean the theory is useless, since it predicts basically anything? Or does it point to something even grander? A multiverse, where every possible shape corresponds to a real, parallel universe, and we just happen to live in one with the right geometry for life? We don't know. But it all comes down to this idea. The key to our reality is hidden in the shape of dimensions we can't see. And that raises the most important question for any theory. Can we ever prove it? The hunt for hidden worlds. No matter how beautiful a theory is, it's just a nice story until you can test it. And for all its promise, this is the biggest hurdle for string theory. So how could we possibly find proof of something so small and so well hidden? The hunt is on, and it's happening on a few different fronts. Our best bet is the Large Hadron Collider, or LHC, at CERN. By smashing particles together at insane speeds, scientists hope they might knock something out of our dimensions and into one of the hidden ones. One clue physicists are hunting for is missing energy. In any collision, the energy you put in has to equal the energy that comes out. If the numbers don't add up after a smash, it would mean something invisible must have carried that energy away, perhaps a particle of gravity escaping into the extra dimensions. So far, we haven't found any definitive proof of that missing energy. Another thing they're looking for is the creation of brand new, exotic particles. These would be heavier cousins of the particles we already know, and finding one where our current theories predict nothing would be a smoking gun for extra dimensions. But after years of searching, the universe has been quiet. But maybe the most spectacular clue, though this is a long shot, would be creating tiny, microscopic black holes. Normally, gravity is way too weak to do this. But some theories suggest gravity is the only force that spreads out through all the dimensions, which is why it seems so weak to us. If that's true, at very tiny distances, gravity would get much stronger. Strong enough that maybe, just maybe, two protons colliding at the LHC could squeeze together and form a teensy black hole, which would instantly evaporate in a burst of particles. The LHC has looked for these explosive events. And again, it's found nothing. So, does this lack of evidence mean the whole idea is wrong? Not necessarily. It could just mean the dimensions are curled up even smaller than we thought, or that we need an even more powerful collider to see them. These null results aren't failures. They're super important clues that tell us which versions of the theory don't work, helping scientists narrow down the search. There are even tiny, tabletop experiments looking for changes in gravity at super short distances. So far, gravity has behaved exactly as expected, putting tight limits on how large these extra dimensions could be. The hunt is far from over, but for now, the hidden worlds remain hidden. So, we started this journey in a world we thought we knew, with 3 simple dimensions. We found ourselves in the middle of a cosmic conflict between our 2 best theories of reality. That conflict is what forces scientists to search for a deeper, unified theory. That search led us to a century-old idea of a 5th dimension. That seed of an idea blossomed into the vast and beautiful landscape of string theory, which says everything is just a vibration. But that elegance comes with a strange price. Our universe can't just have 3 dimensions of space. It needs 9, or even 10. We learned these hidden dimensions could be the architects of our reality, curled up in a complex geometric shape that dictates the laws of physics. It seems our laws of physics might just be a shadow of a hidden geometry. But we have to be honest here. Despite a century of incredible work, we have found zero direct evidence that these dimensions are real. They remain, for now, a beautiful mathematical dream, a ghost in the machine of physics. The experiments have turned up nothing. But that's how science works on the bleeding edge. It isn't a straight line to the answer. It's a messy, frustrating, thrilling exploration of the unknown. The quest for extra dimensions forces us to ask the biggest questions possible. What is space? What is reality? And why is the universe the way it is? So the next time you move through the world forward, backward, left, right, up, down, take a second to wonder if you're also moving along other paths. That folded into the fabric of space, there might be a secret, intricate, multi-dimensional origami that writes the rules for everything we see. We don't have a map for this hidden land yet. We might never get one. But the search for these invisible directions is the ultimate journey to understand the true nature of reality itself. If this journey into the unseen corners of our universe blew your mind, subscribe for more explorations into the biggest mysteries of the cosmos. And let us know in the comments, what other cosmic questions should we try to answer next? Scientists think our universe is a fold in reality. Take a look at your hand. It feels solid, right? The world around you, the chair you're on, the floor beneath your feet, it all feels real and present. But what if it's not? What if this entire, sprawling universe is just one thin layer, a single page folded inside a colossal, hidden reality of 11 dimensions? For decades, this idea, which came out of the wonderfully weird world of string theory, was seen as mathematical fantasy, a dead end for physics. But what if I told you that's starting to change? That after years of silence, scientists are picking up the first faint, tantalizing hints from the cosmos that this impossible reality might actually be true. We're not talking about proof. We're not talking about certainty. We're talking about a new chapter opening in a cosmic detective story that has stumped the brightest minds for a century. The case went cold for a long time, but a few strange new clues have just turned up, and they might just challenge everything we think we know. Our story starts with a crime scene. A fundamental contradiction right at the heart of physics. For more than 100 years, we've had 2 supreme laws of the universe. The first is Albert Einstein's general theory of relativity. It's a majestic, sweeping theory that describes the cosmos on the grandest scales: planets, stars, and galaxies. It's gravity, but reimagined as the elegant warping and curving of a 4-dimensional fabric we call spacetime. And it works perfectly. It predicted that starlight could bend, that black holes were real, and that gentle ripples in spacetime called gravitational waves existed. It is, without a doubt, a masterpiece. The second law is quantum mechanics. This is the law of the very, very small. It's a chaotic, counterintuitive, and frankly mind-bending set of rules for the world of particles. It paints a picture of a universe built on probability, where particles can be in many places at once, and a cat in a box can be both alive and dead until you peek inside. It's bizarre, but it's also one of the most successful and rigorously tested theories in the history of science. Your phone, your computer, the laser scanner at the supermarket, they all work because quantum mechanics is right. And here's the crime. These 2 theories, our 2 pillars of understanding, absolutely despise each other. They can't coexist. When you try to use them together, the universe just breaks. Think about the Big Bang, a moment when the whole universe was infinitesimally small and infinitely dense. You need general relativity for the massive gravity and quantum mechanics for the tiny scale. But when you put them together, the equations spit out nonsense. infinities, paradoxes. The math just completely falls apart. This is the central mystery of modern physics. It's like having two perfect maps, one of the land and one of the sea, but where they meet at the coastline, they describe totally different worlds. This incompatibility is the crime scene that sent physicists on a decades-long hunt for a culprit. A single, unifying theory that could bridge the gap. They call it the theory of everything. And for the last 50 years, there has been one prime suspect. The prime suspect. That suspect is string theory. It didn't show up as some grand solution, but as an accidental discovery in the late 1960s. A young physicist named Gabriele Veneziano was trying to write an equation to describe the strong nuclear force, the glue that holds atoms together. He stumbled upon a 200-year-old mathematical formula called the Euler beta function, and to his shock, it perfectly described the particle interactions he was studying. It was a weird, unexpected connection, and nobody had a clue why it worked. It was a clue without a context. It took a few more years for physicists like Yoichiro Nambu, Holger Nielsen, and Leonard Susskind to realize what was going on. They figured out that this obscure bit of math was actually describing something physical. Tiny, one-dimensional, vibrating filaments of energy. It was describing strings. This was the birth of a radical new idea. What if the basic building blocks of the universe weren't tiny dots, as we'd thought for centuries? What if, when you zoomed way in on an electron or a photon, you found a minuscule, wriggling loop of energy? This is the core idea of string theory. It's both beautifully simple and unbelievably complex. The go-to analogy here is a musical instrument. Think of a cello. One string on that cello can vibrate in different ways to create a multitude of different notes. Pluck it one way, you get a C, another way, you get a G, each note is just a different vibrational pattern. Now, imagine the entire universe is built from one fundamental thing, a tiny, vibrating string. According to the theory, every particle we see, the electron, the photon, the quarks inside a proton, is nothing more than a different note being played on this cosmic string. A specific vibration gives you an electron. A different vibration gives you a photon. All the particles and forces we see are just a symphony of vibrations. The laws of physics are the harmonies, and the universe is a grand, cosmic orchestra. It's a breathtakingly elegant idea. Instead of a messy zoo of different particles, string theory says there's just one thing. The string. It unified all of matter and force into one picture. And most importantly, when physicists explored the math, they found something incredible. Among the many notes the string could play, there was one special vibration with the exact properties of a particle that had been theorized but never found. A massless particle with 2 units of spin. It was the graviton, the hypothetical quantum particle of gravity. For the first time, a theory had naturally included gravity in the quantum world. General relativity and quantum mechanics were finally speaking the same language. The cello was playing both the frantic notes of the quantum realm and the deep, resonant tones of spacetime. String theory wasn't just a suspect for the theory of everything. It was the only suspect that seemed to explain everything. It promised to be the ultimate solution. But this beautiful theory came with a deeply strange story. To work, it needed a stage far grander and weirder than anyone had ever imagined. The suspect's strange world. For the math of string theory to hold together, it made a non-negotiable demand. The universe couldn't just have the 4 dimensions we know, 3 of space and 1 of time. The theory was clear. The universe must have more. Early versions required a wild 26 dimensions. Later, a more sophisticated version called superstring theory brought that number down to a more reasonable 10. 9 dimensions of space and 1 of time. This was, and still is, a huge mental hurdle. Where are they? We move forward, backward, left, right, up, down. We experience time passing. That's it. We don't see a fifth or a ninth spatial dimension. If they're real, why can't we just point in some new direction and step into another reality? String theorists came up with a brilliant idea, best understood with the classic garden hose analogy. Imagine you're on a skyscraper, looking down at a construction site. You see what looks like a long, thin, one-dimensional line. But as you zoom in with binoculars, you see it's actually a garden hose. It has a second dimension. You could travel in a tiny circle around its circumference. From far away, that extra dimension was invisible. But up close, it was there all along. This is the concept of compactification. String theory suggests that the 6 extra spatial dimensions are curled up into an impossibly tiny shape at every single point in our space. How tiny? We're talking about the Planck length, or 10 to the power of minus 35 meters, a million billion times smaller than an atom. They're so small we could never see them or feel them, not even with our most powerful instruments like the Large Hadron Collider. They exist as a complex, 6-dimensional geometric shape, known as a Calabi-Yau manifold, woven into the fabric of reality. The precise shape of these curled-up dimensions determines how the strings vibrate, which in turn sets the fundamental constants of our universe, like the mass of an electron or the strength of gravity. Things got even weirder in the mid-1990s. Physicists, led by figures like Edward Witten, realized that the 5 competing versions of string theory were all just different views of a single, deeper theory. It was like 5 people describing an elephant in the dark. One feels a trunk, another a leg, but they're all touching the same animal. Witten called this deeper framework M-theory. And M-theory added one more spatial dimension, bringing the total to 11. More importantly, it wasn't just a theory of strings. It also included higher dimensional objects called branes, short for membranes. This led to a radical new idea. What if our entire universe is stuck on one of these branes? Imagine our universe as a vast, 3-dimensional sheet of paper. All the particles and forces we know, electrons, light, everything, are like ink on the paper. They can move anywhere on the sheet, but they can't leave its surface. This 3-brane is our home. But M-theory proposed one thing wasn't stuck to the brane: gravity. The graviton is a closed loop of string, not an open one with its ends tied to our brane. And because it's a closed loop, it's free to travel. It can leak off our brane and journey into the full, 11-dimensional space, called the bulk. This offers a startlingly elegant explanation for why gravity is so much weaker than the other forces, about 10 to the power of 36 times weaker. The other forces are concentrated on our brane, but gravity's strength is diluted because it's spread out across all the extra dimensions. We only feel a tiny fraction of its true power. This is the folded reality from our title. Our universe isn't everything. It's just a slice, a 3-brane, floating in a higher dimensional hyperspace. There could be other universes, other branes, floating parallel to our own, maybe just millimeters away in another dimension, yet totally invisible to us. The only way we could ever interact with them is through the faint whisper of gravity leaking across the void. This was the breathtaking story the theory told. It solved everything. There was just one problem. There wasn't a single shred of evidence. The cold case. For any scientific theory to be taken seriously, it has to make predictions you can actually go out and test. For decades, this has been string theory's biggest problem. The energy you'd need to see the strings themselves or probe these tiny extra dimensions, the Planck energy, is a quadrillion times higher than what our most powerful particle accelerator, the Large Hadron Collider, LHC, can reach. Building a machine that powerful would require an accelerator the size of a galaxy. It's just not going to happen. This lack of evidence divided physicists. Supporters argued that its mathematical beauty and power to unite physics made it the only real candidate for a theory of everything. Critics dismissed it as a philosophical fantasy, a theory that couldn't be proven wrong and was therefore not even science. The situation got even messier with the discovery of the landscape. It turns out there isn't just one way to curl up those 6 extra dimensions. The math suggests there could be as many as 10 to the power of 500 possible ways, each creating a different universe with different laws of physics. If your theory allows for 10 to the power of 500 possible outcomes, how can it predict anything about our universe? It's so vague it becomes useless. For many, this was the final straw. The excitement of the 90s faded, and the case for the theory of everything went cold. Hopes were pinned on the LHC. While it couldn't see strings, maybe it could find indirect clues. The 2 big things scientists looked for were supersymmetry, the idea that every known particle has a heavier superpartner, and evidence of the extra dimensions themselves. If the brane world idea is right, one possible sign could be energy seeming to vanish from a particle collision, as a graviton escapes our brane into the bulk. An even wilder idea was the creation of tiny, harmless black holes that would instantly evaporate. For years, the experiments ran. Trillions of protons were smashed together. But the results were nothing. No super partners. No definitive signs of escaping gravitons or micro black holes. To be clear, the analysis of all the data isn't over, and there's always hope for the future. But as of early 2026, the LHC has found no conclusive evidence of physics beyond our current standard model. For many, it felt like the trail had gone completely cold. Or so it seemed. Because while the high-energy frontier was quiet, strange whispers started coming from a completely different direction, not from smashing particles, but from staring out at the cosmos. A new lead? The new clue comes from the biggest mystery in modern cosmology: dark energy. Back in 1998, astronomers discovered the expansion of the universe is speeding up. Something is pushing space apart, acting like anti-gravity. We call this dark energy, and it makes up 70% of the universe. For decades, the best explanation has been that it's a cosmological constant. A steady, unchanging energy baked into the vacuum of space itself. But recent observations have started poking holes in that simple picture. The Dark Energy Spectroscopic Instrument, or DESI, has been building a massive 3D map of the universe. Its latest results hint that dark energy might not be constant. The data suggests its influence might be evolving, possibly weakening over time. Now, we have to be really careful here. This is not yet a revolutionary discovery. The evidence is still preliminary, at a statistical level that makes physicists intrigued, but not certain. The results are also, for the most part, still consistent with the standard model. But the hint is there, and it seems to be getting a little stronger as more data comes in. This is where, unexpectedly, string theory walks back into the room. A few years ago, the prominent string theorist Qumran Vafa and his colleagues proposed a set of rules, called the swampland conjectures, to sort out which kinds of universes are possible in string theory. One of the most startling conjectures was that a universe with a stable, constant dark energy like the one in our standard model is in the swampland. It's forbidden. Instead, string theory seems to require that dark energy must change over time. It has to decay. Suddenly, the strange new data from DESI, hinting at a weakening dark energy, seems to resonate with this once obscure prediction from string theory. This doesn't prove string theory is right. There could be other explanations. But it's a striking correlation, the first in a long time where a major cosmological observation appears to favor the kind of universe string theory predicts over the standard one. And if you go to the most remote, abstract frontiers of theoretical physics, you find other ideas brewing. For example, some highly theoretical work by physicists like Richard Pinsick explores the idea that the hidden dimensions themselves aren't static but have an intrinsic twist to them, a property called torsion. In this speculative model, the twisting and untwisting of these hidden dimensions is what gives particles their mass. But let's be upfront. This is extremely speculative stuff. It's not mainstream or verified. It's an example of how the asterisk language of string theory is being used to find new ways of thinking about old problems. These ideas, from cosmic surveys to abstract math, represent a potential shift. For decades, the knock against string theory was that it didn't connect to the real world. Now, we have threads, however tentative, that connect the suspect's strange story to the clues we're finding at the crime scene. The case remains open. So, where does that leave us? Have we proven our universe is a folded reality in 11 dimensions? Absolutely not. String theory is still a work in progress, not an established fact. The big searches at the LHC have so far come up empty, and the intriguing hints from cosmology are still just hints. The case is far from closed. But something has shifted. The idea that string theory is a dead-end project is being challenged. The theory is finding new relevance, not as a single final equation, but as a powerful language for asking profound questions about the universe, with unexpected applications in fields from black holes to mathematics. We are cosmic detectives, trying to piece together a story of unimaginable scale. We started at a crime scene, the conflict between our two greatest theories of physics. We found a prime suspect, string theory, with a story that was elegant but seemed like pure fantasy. For years, the investigation stalled due to a total lack of evidence. But now, new leads have appeared. Faint signals from the cosmic dark that point to a universe behaving in a way the suspect said it should. These are not confessions. They are not smoking guns. They are whispers. Possibilities. But in a cold case that's lasted for half a century, a whisper can be deafening. The ultimate nature of reality is still the greatest mystery of all. Are we living on a delicate membrane, a single fold in a reality so vast and complex our minds can barely grasp it? We don't have the answer. But the investigation is active again. The case file is back on the desk, and for the first time in a long time, it feels like we might be on the verge of pulling back the curtain, just a little, to glimpse the true architecture of our cosmos. But what do you think? Is string theory a beautiful dead end, or is it pointing toward the ultimate truth? Did the cello analogy click for you, or did the garden hose make more sense? Let us know in the comments below. We read them all, and your questions often spark our next investigation. If you enjoyed this journey to the edge of reality, please consider subscribing. Your support helps us continue to explore these big questions. Thanks for watching, and as always, stay curious. You are living in 11 dimensions and you don't know it. What if the floor beneath your feet, the chair you're sitting on, and the very air you're breathing? What if all of it is just a tiny piece of the real world? What if, right now, you're living and moving through a universe with 11 dimensions, but you're only built to see 3 of them? It might sound like science fiction, but it's a real possibility that physicists have been wrestling with for decades. The reality you experience every day? It might not be reality at all, but just a sliver of a much larger, and far stranger, cosmos. The walls of your room might not be the end of your space, they might just be the beginning of everything else. Go on, take a look around. You see a world of length, width, and height. You can move forward and back, left and right, up and down. These are the 3 spatial dimensions that define our existence. They're intuitive, familiar, and for a long time, we thought that was the whole story. For centuries, this was our picture of the universe. A 3-dimensional stage where the drama of life plays out. But that tidy picture started to fall apart over a century ago. It began with the simple idea that there's another dimension we're always traveling through, one we can't see but can definitely feel. time. Adding time as a fourth dimension turned our view of the cosmos into a four-dimensional spacetime. But physics was just getting started. As scientists dug deeper into the fundamental laws of nature, they ran into some serious mysteries. The biggest one? It's a question of strength. See, there are four fundamental forces that run the show. The strong nuclear force that holds atoms together, the weak nuclear force that governs radioactive decay, electromagnetism that powers our world, and gravity, the force keeping your feet on the ground. Three of these forces fit together beautifully in what's called the standard model of particle physics. But gravity is the odd one out. It's shockingly, almost ridiculously, weak compared to the others. Think about it. A tiny refrigerator magnet can lift a paperclip, its electromagnetic force easily overpowering the gravitational pull of the asterisk entire planet beneath it. This is what physicists call the hierarchy problem, and it's one of the biggest unsolved puzzles in science. So why is gravity so feeble? The hunt for an answer has led physicists down a rabbit hole of mind-bending ideas, but the most persistent and promising of them all is the theory of extra dimensions. The idea that our universe has hidden layers, curled up all around us, just too small for us to see. This is your guide to that hidden world. We're going on a journey, dimension by dimension, to see why so many of the world's leading physicists are convinced that our reality is woven from 11 dimensions. We'll explore how these hidden realms could solve the deepest mysteries of the cosmos. So, forget what you think you know. The world is about to get a whole lot bigger. The first leap, beyond space-time. Our journey starts with a dimension we know but often forget: time. We can't point to it, but we move through it every single second, always in one direction: forward. When Albert Einstein came up with his theory of relativity, he showed that space and time aren't separate things, but are woven into a single 4D fabric called spacetime. Your location isn't just your coordinates in space, but your coordinates in space and time. You're not just at home. You're at home right now. This was the first major upgrade to our dimensional worldview. But the first clue that there might be even more came soon after, back in the 1920s, from a physicist named Theodore Kaluza. Kaluza was trying to unite Einstein's new theory of gravity with the only other force they knew well at the time: electromagnetism. Just for fun, he took Einstein's four-dimensional equations and rewrote them for 5 dimensions. And then something incredible happened. Out of the math for a 5-dimensional universe, 2 sets of laws popped out. One was Einstein's original theory of gravity. The other was, unbelievably, the exact equations for electromagnetism. It seemed too good to be true. The 2 known forces of nature looked like 2 sides of the same coin, but only if you assumed a 5th dimension existed. This led to a pretty obvious question. If this 5th dimension is real, where is it? A physicist named Oscar Klein had a brilliant answer. He suggested the 5th dimension isn't big and expansive like ours. Instead, it's curled up into a tiny circle at every single point in space. This is where we get the most famous analogy in all of physics: the ant on a garden hose. Imagine you're looking at a garden hose from far away. It just looks like a one-dimensional line. But if you were an ant standing on that hose, you'd see things differently. You could walk forward and backward along the hose, sure, but you could also walk around it. For the ant, the hose is a 2-dimensional surface. Klein proposed that the 5th dimension is like the loop of that hose, except it's curled up to an impossibly tiny size billions of times smaller than an atom. So at every point in the space around you, there's a tiny, hidden circle, a direction you could move in, but it's so small we have no idea it's there. Now, that original Kaluza-Klein theory wasn't perfect. It made some wrong predictions about particles. But it introduced a revolutionary idea: that hidden dimensions could explain the laws of physics, and that we don't see them because they're compactified or curled up into a space too small to notice. The door was now open, and physics was about to step into a much, much bigger universe. The symphony of strings. Welcome to 10 dimensions. For a few decades, extra dimensions were a cool but fringe idea. Then, in the 1970s and 80s, they came roaring back with the arrival of a new, wildly ambitious theory: string theory. The basic idea is simple and beautiful. It says that if you could zoom in on any fundamental particle, an electron, a quark, anything, you wouldn't find a little point. You'd find a tiny, one-dimensional, vibrating loop of energy. A string. In this theory, all the different particles are just different notes played on these strings. Just like a violin string can vibrate at different frequencies to make different sounds, these tiny strings can vibrate in different patterns. A string vibrating one way might look like an electron to us. The same string vibrating another way would be a photon. And a string vibrating in yet another pattern would be a graviton, the particle that carries the force of gravity. With this one elegant idea, the entire zoo of particles and forces could be explained as just the music of these vibrating strings. It was a vision of cosmic harmony, a possible theory of everything. But there was a catch. A big one. As physicists worked through the math, they found it came with a non-negotiable demand. For the theory to be mathematically consistent, the universe couldn't just have 4 dimensions. The most promising versions of the theory, the ones without weird paradoxes, required the strings to have more room to vibrate. Specifically, they needed a universe with *10 dimensions *9 of space and 1 of time. This wasn't something physicists just added in, it came right out of the core equations. Without 10 dimensions, the math would break, giving nonsense results like probabilities over 100%. String theory didn't just suggest extra dimensions, it demanded them. So, once again, where are they? Just like before, the answer was that they must be curled up. But this time, it wasn't just 1 extra dimension. It was 6. This is much harder to picture than a simple circle. Trying to imagine 6 hidden dimensions is basically impossible for our brains. But mathematically, physicists could describe them. They proposed that at every point in our 3D space, there exists a tiny, fantastically complex, 6-dimensional shape. These shapes are known as *Calabi-Yau manifolds. They are intricate, beautiful geometric forms, and they are the proposed hiding place for those extra 6 dimensions. Imagine our universe as a loaf of bread. A slice is our 3D world. But embedded at every single point within that slice is a microscopic crumb of this complex, 6D geometry. And here's the truly wild part. The exact shape of that tiny hidden space is everything. The specific geometry of the Calabi-Yau manifold, its twists, folds, and holes, determines how the strings can vibrate. This means the laws of physics we see are a direct result of the shape of these hidden dimensions. The mass of an electron, the strength of a force, all of these fundamental constants are, in theory, written in the geometry of this hidden space. If the Calabi-Yau manifold had a different shape, the strings would vibrate differently, and we'd live in a universe with totally different laws. Now, let's be honest here. For all its beauty, string theory is still a theoretical framework. It hasn't been proven by any experiment. The strings and curled-up dimensions are thought to be so small they're far beyond our current technology to see directly. But the idea that our reality is shaped by hidden geometry had become a central pillar of modern physics. And the story was about to get even weirder. The unifying theory, M-theory, and the 11th dimension. By the early 1990s, string theory was having a bit of an identity crisis. It turned out there wasn't just one theory, but 5 of them. 5 different, consistent versions of string theory, all describing a 10-dimensional universe, but each one slightly different. This was a headache for physicists looking for a single theory of everything. Which one was right? The breakthrough came in 1995 from a physicist named Edward Witten. He suggested that the five-string theories weren't competing at all. Instead, they were all just different views of a single, deeper theory, one that existed in *11 dimensions. He called this master framework M-theory. The M is said to stand for mystery, magic, or membrane. Witten has been coy, but membrane is probably the most helpful one. Because M-theory adds a new character to the story. On top of one-dimensional strings, it includes higher-dimensional objects called branes. Brane is just short for membrane. A1 brane is a string. A2 brane is a two-dimensional sheet. A3 brane is a three-dimensional volume, and so on. And this is where our picture of reality really flips on its head. One of the biggest ideas from M-theory is the brane world concept. In this scenario, our entire universe, everything we see and touch, might just be a 3-brane, a 3D island floating in a huge, 11-dimensional space, often called the bulk. Think of it like the surface of a pond. For creatures living on that 2D surface, that's their whole world. They wouldn't know about the 3D bulk of the water below. In the brane world idea, our universe is like that 2D surface. We are stuck on a 3-brane. In this model, all the particles that make up our world, electrons, photons, quarks, are like the open ends of strings that are physically stuck to our brane. They can move around in our 3 dimensions, but they can't leave. This would explain why we only experience 3 spatial dimensions. But there's one huge exception: gravity. In M-theory, gravity is caused by closed loops of string. And unlike the open strings, these closed loops aren't tied down to our brane. They are free to travel through all 11 dimensions, both on our brane and off into the bulk. This provides a stunningly elegant solution to the hierarchy problem, that mystery of why gravity is so weak. In this model, the reason gravity feels so feeble is because most of it isn't even here. It's leaking away into the extra dimensions. We only feel a tiny fraction of its true strength. The other forces feel so much stronger because they are completely confined to our 3-brane, right here with us. It's a mind-bending idea that our entire cosmos is just a slice of a bigger reality, and that gravity is just a faint whisper from a higher dimensional space. M-theory is not a proven fact, but its ability to unite the other theories and potentially solve one of physics' deepest puzzles makes it the leading candidate for a theory of everything. So the question becomes, how could we ever find out if it's true? Hiding in plain sight, searching for the dimensions. So, we have this incredible theory, an 11-dimensional universe where we live on a 3-brane. It's a great story, but without evidence, that's all it is. How could we ever prove these extra dimensions are real? The answer is to look for things that could only happen if they exist. Our best tool for the job is the Large Hadron Collider, or LHC, at CERN. The LHC smashes protons together at nearly the speed of light, recreating the insane energies of the early universe. If extra dimensions are real, they might leave tiny fingerprints in the debris from these collisions. There are a few key things physicists are looking for. The first is something called Kaluza-Klein particles. Remember the ant on the hose? A particle moving around that tiny, curled-up dimension would have extra momentum, which from our perspective, would look like extra mass. So, these theories predict that for every particle we know, there should be a whole tower of heavier echoes. For instance, a heavier version of the Z boson, sometimes called a Z-prime. Finding a particle like that at the LHC would be a smoking gun for extra dimensions. Another clue would be missing energy. Collisions at the LHC are perfectly balanced explosions. The energy flying out has to equal the energy that went in. But if a collision creates a particle that can leave our brane and escape into the bulk like a graviton, it would just vanish from our detectors. We wouldn't see the particle, but we would see an imbalance. It would look like energy just disappeared. That, missing Energy could be our first direct sign of something escaping into the bulk. Maybe the most spectacular, though unlikely, signal would be creating microscopic black holes. In our familiar dimensions, it takes immense energy to make a black hole. But if extra dimensions exist, gravity might get much stronger at very tiny distances. Strong enough that high-energy collisions at the LHC could create quantum-sized black holes. These aren't cosmic monsters. They'd evaporate almost instantly in a unique burst of radiation that our detectors could spot. Seeing that would be an earth-shattering discovery. So, have we found any of this? As of early 2026, the honest answer is no. After years of searching, the LHC has not found any definitive evidence for extra dimensions. This isn't a failure, it's just part of science. What does finding nothing mean? It tells us where not to look. The fact that we haven't found these particles tells us that if the dimensions are real, they must be curled up even smaller than some models predicted, needing more energy to access than even the LHC can provide. The search has ruled out the simpler models and sent theorists back to the drawing board. And that search is far from over. The LHC is always being upgraded, and the hunt for hidden dimensions remains one of the top goals in physics. The clues could be right around the corner, or they might require a new, more powerful collider to finally find. For now, the dimensions remain hidden, but the search goes on. A new kind of reality. Dimensions as geometry. So far, we've talked about extra dimensions as a tiny room for particles to vibrate in or for gravity to leak into. But what if they're more than just a passive stage? What if the very geometry of these hidden spaces is what creates the properties of matter itself? This takes us to the cutting edge of theoretical physics. While the Higgs boson is the confirmed explanation for how particles get their mass, some physicists are exploring radical alternatives rooted in pure geometry. Some of these cutting-edge models are exploring what happens when the geometry of the extra dimensions is allowed to change and twist over time. The idea is that this hidden geometry isn't static. It can flow and even possess a kind of built-in twist. In these models, as this hidden shape evolves, it can settle into a stable, twisted form. Here's the mind-blowing part. Calculations suggest that as particles like the W and Z bosons move through spacetime, they would feel a kind of resistance or drag from this twisted background, and this resistance would be what we experience as mass. In this picture, mass isn't something given to a particle by an external field. Instead, matter gets its properties from the resistance of geometry itself. It's a huge shift in perspective. The properties of particles wouldn't come from other particles, but from the very shape of the hidden dimensions they live in. This kind of idea also offers a potential hint at another cosmic mystery: dark energy. The math suggests that the curvature created by this twisted geometry could be responsible for the accelerating expansion of our universe. This is all highly speculative, living on the absolute frontier of physics. It hasn't been proven. But it represents a powerful new way of thinking. Extra dimensions might not just be hiding places. They could be the architects of reality, with their geometry dictating the laws of physics and the properties of matter in our world. It's a vision of a universe built not from particles, but from pure, dynamic geometry. If your mind is bending right now, do me a favor and hit that like button. It tells the algorithm you're enjoying this trip into the unknown. Now, what if these dimensions don't just give particles mass, but create the very boundary of our universe? The edge of everything, boundaries and the bulk. The idea that we live on a brine floating in a higher dimensional bulk leads to another deep question. Does our universe have an edge? This puzzle comes into sharp focus when we look at the most extreme objects in the cosmos: black holes. A black hole has a point of no return called an event horizon. According to Stephen Hawking, black holes aren't truly black, they slowly evaporate by emitting Hawking radiation. But this created a 50-year-old problem: the asterisk black hole information paradox. Quantum physics demands that information can never be destroyed. Every detail about what falls into a black hole has to be preserved. Yet Hawking's calculations showed the radiation coming out is random. It carries no information. So when the black hole vanishes, where did the information go? It seems to have disappeared from the universe, breaking a fundamental law of physics. One of the most promising solutions to this paradox is an idea that sounds like pure sci-fi: the asterisk holographic principle. Proposed by physicists Gerard T. Hooft and Leonard Susskind, it suggests that all the information inside a volume of space, like the 3D interior of a black hole, can be completely described by a theory living on the 2D boundary of that space. It's like a security hologram on a credit card, where a flat, 2D surface contains all the information to create a 3D image. For a black hole, this means the information about whatever fell in isn't lost inside. It's stored on the 2D surface of the event horizon. As the black hole evaporates, that information is subtly released back out, solving the paradox. The information was never truly inside the 3D space to begin with. Now, let's take that wild idea and apply it to the whole universe. A concept called the ADS-CFT correspondence gives us a concrete mathematical example of this. It proposes that a theory of gravity in a certain kind of 5-dimensional, bulk, space is mathematically identical to a quantum theory without gravity living on the 4-dimensional boundary of that space. This is a stunning duality. It means there could be two totally different ways of describing the same reality. One with gravity and extra dimensions, the other with quantum particles on a lower dimensional boundary, without gravity. They are two different languages telling the same story. This could mean that our universe, our 3 brane with all its quantum weirdness, is a holographic projection of laws taking place on a distant, higher dimensional boundary. We could be the hologram. This isn't just a fun idea. The ADS-CFT correspondence is a serious and powerful tool in theoretical physics. While it doesn't prove our universe is a hologram, it shows the idea is mathematically sound. The edge of our universe might not be a place you can visit, but an informational boundary that defines reality itself. The edge of everything might be everywhere. We've taken a journey to the absolute edge of theoretical physics. We started in our familiar 3D world, added time, and then saw how the hunt to unite the forces of nature led to a 5th dimension, curled up and hidden. That thread led us to string theory's 10-dimensional universe, where the laws of physics are written in the geometry of hidden shapes. And finally, we landed at M-theory, with its 11 dimensions and the mind-bending idea that our entire cosmos might be a membrane floating in a larger reality. We've explored how these strange ideas could solve some of our deepest mysteries. Why gravity is so weak, how particles get mass, and how to solve the black hole information paradox. We've seen that these hidden dimensions might be the very architects of our world. So, are any of these wild ideas true? The honest answer is, we don't know. Not for sure. These are magnificent sandcastles of thought, built by the human mind on the shore of the cosmic ocean. Right now, we have no direct proof that these extra dimensions are real. The search continues at the LHC and in the minds of theorists everywhere. But the fact that these ideas keep showing up in our most advanced mathematics tells us we have to take them seriously. So the next time you look around your room, remember what you've learned. You might not be seeing the whole picture. The solid world you feel might be just one layer of a far more complex reality. You could be living in a universe far grander and more mysterious than you ever imagined. The walls of your reality might just be the beginning. What do you think? Are we living in a simple 4D spacetime, or are we part of a grander, 11-dimensional cosmos? Let me know your thoughts in the comments. And if you want to keep exploring the biggest questions in the universe, make sure to subscribe and ring that bell. Your brain is lying about the edge of the universe. Your brain is lying to you about the edge of the universe. Seriously. When you try to picture the cosmos, you probably imagine a giant box or maybe a sphere with something outside of it. You feel an almost irresistible urge to ask, so, what's beyond the boundary? That feeling, that mental picture, is a fundamental mistake. It's an illusion, a profound error cooked up by the very part of your mind that helps you navigate the everyday world. It feels real, it feels logical, but it is deeply, fundamentally wrong. In this video, we're going on a journey to tear down that illusion, piece by piece. We'll explore how your own language and your built-in 3D perception trick you into asking the wrong questions about reality. And then, we'll travel together to the real edge. Not an edge of space, but an edge of what we can possibly know. By the end, the question, what is the universe expanding into, will feel as nonsensical as asking, what is north of the North Pole? You'll see the universe not as a container, but as something far stranger, more elegant, and infinitely more awe-inspiring. The root of the lie, your brain's broken GPS. Before we head out into the cosmos, we have to start right here, inside our own heads. Because the lie isn't born in the depths of space, it's born in the architecture of our minds. Your brain is a survival machine, honed over millions of years to do a few things exceptionally well: find food, avoid becoming food, and navigate a pretty small, three-dimensional environment. It's a master of up versus down, inside versus outside. It built a world of containers and boundaries. A cave has an inside and an outside. A forest has an edge. A box has walls. Our entire physical experience is built on this framework. We exist in a room, on a planet, within a solar system. This way of thinking is so hardwired into our neural pathways that our very language reflects and reinforces it. Think about the words we use: in, out, above, beyond. These prepositions are the building blocks of how we structure reality, and they inherently assume a container and a context. So when we ask, what is outside the universe? The lie is already baked into the question. The word outside forces us to imagine the universe as an object inside a bigger, imaginary box before we've even started thinking. It's like a character in a video game trying to ask what's beyond the screen. To that character, the world is the code, the rendered environment. There is no beyond the screen. That concept doesn't exist in their reality. The question itself is a category error. Their senses are confined to the rules of their world. They can't step out of the game because their reality is the game. In the same way, we're trying to use the logic of our three-dimensional game to understand the game engine itself. This intuitive trap is incredibly powerful. We're like fish who have no concept of wet. We are so completely immersed in our 3D perception that we don't even recognize it as a lens. We mistake the lens for reality itself. We think in straight lines and simple shapes because that's what our survival depended on. Our brain is a brilliant navigator of the Serengeti, but it's a terrible guide to the fundamental nature of spacetime. It just wasn't built for that. It wasn't designed to intuitively grasp a four-dimensional manifold or a universe where parallel lines can meet. So, when we look at the night sky and get that feeling of a vast, dark room with walls we can't see, that's not a cosmic insight. That's our terrestrial, cave-dwelling, box-stacking brain imposing its limited operating system on a reality that has no obligation to conform to it. The feeling that the universe must have an outside isn't a logical deduction. It's an artifact of our own cognitive limits. It's a ghost in our mental machine. To understand the universe, we first have to admit our built-in GPS is broken. The first step to finding the truth is to stop trusting the lie our own mind is telling us. The journey outward, deconstructing the lie, layer by layer. To really dismantle this illusion of an edge, we need to retrace our cosmic journey, starting from the familiar and moving outward, step by step. At each stage, we'll see how a previous edge turned out to be nothing more than a failure of imagination. Our journey starts right here, on Earth. For most of human history, it was just common sense to believe the world was flat. It looked flat. The horizon looked like an edge. It was perfectly logical to ask, if I sail far enough, will I fall off? The edge of the world was a real and terrifying concept. But it was a lie, an illusion created by perspective and scale. When explorers finally circumnavigated the globe, they didn't fall off. They didn't hit a wall. They just came back to where they started. They discovered that the Earth is a finite surface without a boundary. It's a closed 2D surface, a sphere. You can travel on it forever and never find an edge, because no edge exists. This is our first and most important clue. The universe might be playing the exact same trick on us, just on a much grander scale. Now, let's zoom out. We leave the Earth behind. We drift past our solar system. Here, our intuition is still mostly comfortable. We see huge distances, but it all still feels contained. Our galaxy, the Milky Way, feels like a city of light in the dark. Beyond it, other galaxies appear as fuzzy islands. Our brain's old habits kick in again, seeing these galaxies as objects within a larger, empty space. The lie whispers that all this must be happening inside something. But this is where our intuition starts to break. In the 1920s, astronomers like Edwin Hubble discovered that almost every galaxy was moving away from us. And the farther away a galaxy was, the faster it was receding. This gave birth to the Big Bang theory, but it also cemented one of the biggest misconceptions in all of science. When we hear explosion, we picture a bomb going off, fragments flying from a center point into an empty room. So, we think of the Big Bang as a point in a black void, with matter rushing out to fill it. And if it's filling a void, there must be an edge to the expanding cloud. But this is completely wrong. The Big Bang was not an explosion in space. It was the expansion of space itself. This is where we need cosmology's most famous analogy, the inflating balloon. Imagine you draw dots on a deflated balloon. Each dot is a galaxy. Now, inflate it. From the perspective of any single dot, all the other dots are moving away. The dots farther away seem to move faster. There's no center of the expansion asterisk on the surface of the balloon. The expansion happens everywhere at once. The galaxies aren't moving through space. They're being carried along as the fabric of space itself stretches. This is what's happening to our universe. Space itself is expanding. This single idea shatters the notion of the universe expanding into anything. There is no empty room outside the balloon. The balloon is the universe, in this 2D analogy. Asking, what is it expanding into, is to fundamentally misunderstand what's happening. Albert Einstein's own theory of general relativity predicted this dynamic, moving cosmos. The expansion isn't a wave moving through water. It's as if the water itself is being created between every 2 points. Understanding this is the key that unlocks the real nature of the universe's edge. The edge, re-examined, the solution in plain sight. So, if there's no physical wall, what do scientists mean when they talk about the edge of the universe? This is where we stop deconstructing the lie and start understanding the beautiful, subtle truth. The edge you've heard about is real, but it's not an edge in space. It's an edge in asterisk time. It's the boundary of the asterisk observable universe. Imagine you're on a ship in a vast, dark ocean. The light from your lantern travels outwards. You can only see things your light has had time to reach and reflect back from. There's a horizon around you, a limit to your vision. But you know there's more ocean beyond that horizon. The horizon isn't a wall. It's a boundary of information, defined by the speed of light. The observable universe works exactly the same way. The universe is about 13.8 billion years old. Light travels at a finite speed. This means we can only see objects whose light has had enough time in those 13.8 billion years to reach us. But here's the twist. While light from a distant galaxy has been traveling for billions of years, the space between us and that galaxy has been expanding the entire time. Because of this, the actual edge of what we can see is now about 46.5 billion light years away. This is our cosmic horizon. It's our personal bubble of information. Every location in the universe has its own unique observable universe. It's profoundly misleading to call it the edge of the universe. It's just the edge of our view. There is almost certainly more universe beyond it. We just can't see it yet. This solves the paradox of the edge, but it opens up an even cooler question. What is the overall shape of the entire universe? Is it finite or infinite? To figure this out, cosmologists look at the oldest light in the universe, the cosmic microwave background. By studying its properties, missions like the Planck satellite have tried to measure the overall curvature of space. Based on that data, there are three main possibilities. First, the universe could be flat. In this context, flat just means it follows the rules of geometry you learned in school. Parallel lines stay parallel forever. If the universe is flat, it's most likely infinite. Our observable universe is just a tiny patch of an infinitely vast reality. Current data suggests the universe is astonishingly, mind-bogglingly close to being perfectly flat. Second, the universe could have a positive curvature making it closed, like a sphere, but in 3 dimensions, a hypersphere. In this universe, space would be finite but have no boundary. If you flew in a straight line long enough, you'd eventually loop back to where you started. Third, the universe could have a negative curvature making it open, like a saddle. In this case, parallel lines would eventually diverge, and the universe would be infinite, just with a different geometry. Notice what all 3 plausible scenarios have in common. None of them have a physical edge you can crash into. The lie our brain tells us the image of a box is nowhere to be found in the actual physics. The solution to the paradox of the edge is that there is no paradox. The edge was never there. Beyond the lie, peeking into higher dimensions, we've dismantled the illusion of a physical edge and replaced it with a real horizon of observation. We've seen that the universe's overall shape doesn't need an outside. But now the journey gets really weird, right at the frontier of theoretical physics. What if the question isn't, what is outside our universe? But rather, what deeper structure is our universe a part of? This is the world of string theory and extra dimensions. For decades, some physicists have proposed that our universe isn't just the 3 dimensions of space and 1 of time that we experience. In string theory, these extra dimensions are required for the math to work, often postulating 10 or 11 dimensions total. They aren't an outside we can visit, but a microscopic, geometric landscape curled up trillions of times smaller than an atom. A grander idea is called brane cosmology. In this picture, our entire 4-dimensional universe is like a giant membrane, or brane, floating within a higher dimensional space called the bulk. We, and all the particles and forces that make up our reality, are stuck to this brane. We're like drawings on a single sheet of paper, unable to perceive the other sheets or the 3D room they're in. This is where it gets compelling. In some of these models, one force is special, gravity. While other forces are stuck to our brane, gravity is thought to be able to leak out into the higher dimensional bulk. This could elegantly explain one of physics' deepest mysteries. Why is gravity so much weaker than other forces, like electromagnetism? A tiny fridge magnet can beat the gravitational pull of the entire Earth. In brane theory, the answer could be that gravity's strength is diluted because it's spread across those extra dimensions. This idea completely reframes the question of an outside. It suggests the reality we perceive is just a shadow, a lower dimensional projection of a much more complex geometric machine. We would be structurally contained within a much larger, higher dimensional reality. This isn't just wild speculation. Physicists are actively looking for evidence. Experiments at particle colliders like the Large Hadron Collider could potentially create phenomena that would only make sense if energy were escaping into extra dimensions. For instance, if a collision created a graviton, the hypothetical particle of gravity, it might vanish from our dimensions, leaving behind an imbalance in energy and momentum that detectors could spot. So far, no such evidence has been found, but the search continues. We're moving from asking questions based on our faulty 3D intuition, what's beyond the edge, to asking questions based on math and observation. What is the fundamental geometry of reality, and how can we detect it? We aren't looking for a wall at the end of a cosmic street. We're looking for the faint echoes of higher dimensions in the behavior of particles. The lie of the edge was a dead end. But the truth of a universe embedded in a deeper structure opens up a landscape of possibilities that is infinitely more exciting. If this journey beyond your intuition has expanded your own universe of thought, consider subscribing and hitting the notification bell. We dive into these cosmic rabbit holes every week. And letting us know what you thought in the comments really helps us understand what questions you want to see answered next. Your curiosity is what fuels these explorations. So, let's go back to where we started. That feeling, that image in your head of the universe as a box. We've taken a long, strange trip to see why that picture, as natural as it feels, is a profound illusion. We saw that our brains, built for survival on a flat-seeming world, hardwired us with a logic of containers and boundaries that just doesn't apply to the cosmos. We learned from our ancestors' mistake about the edge of the world, realizing that a finite space doesn't need an edge. We confronted the biggest misconception of all, that the Big Bang was an explosion in space, and replaced it with the far more wondrous idea of an expansion of space itself. We saw how that makes the question, what is the universe expanding into, meaningless. We then redefined the edge, transforming it from a fictional wall into a real horizon in time, the boundary of what we can see, not what exists. And finally, we peeked over that horizon with our theories, contemplating the breathtaking possibility that our universe is just a slice of reality, a brane, contained within a higher dimensional structure we can't directly perceive. The universe isn't a box. It's either an infinite, flat expanse, a finite but unbounded hypersphere, or a shadow cast by a reality with more dimensions than we can sense. In every plausible scenario, the lie our brain tells us dissolves into a truth that is vastly more complex, elegant, and beautiful. Letting go of the illusion of the edge isn't a loss. It's an upgrade. It allows us to stop asking the wrong questions and start marveling at the sheer, mind-bending strangeness of a reality so much grander than our intuition could ever have imagined. The universe isn't lying to you, your brain is. And knowing that is the first step towards seeing things as they really are. Scientists believe our universe is inside a black hole. We think of them as the ultimate cosmic monsters. Points of no return, lurking in the dark, waiting to devour anything that strays too close. They're the universe's destroyers, the final, violent end to a star's life. But what if we've got them completely wrong? What if the most destructive things in the universe are actually creators? This isn't just a wild late-night thought. It's a genuine scientific hypothesis, an idea being explored by physicists that suggests our entire universe, everything we know, see, and are, is tucked away inside the event horizon of a massive black hole. And even stranger, it implies that every black hole we see in our own sky could be a doorway to a new universe, maybe one a lot like ours. It sounds impossible, like something pulled from a science fiction novel. But as we're about to find out, this isn't just a guess. It's an idea built on a trail of baffling clues, weird coincidences, and deep connections within the math that describes our reality. It's a theory that tries to answer some of the biggest questions we have. What happened before the Big Bang? Why does time only move forward? And where did the laws of physics even come from? Tonight, we're going on a cosmic detective story. We'll follow the evidence, from the Big Bang itself to the bizarre, twisting frontiers of theoretical physics. We'll look at the clues that support this incredible idea, and we'll face the scientific arguments that push back against it. By the end, how you see reality, the night sky, and your own place in it, might just be changed for good. The briefing, our cosmic cast of characters. Before we can crack a cosmic mystery this big, we need to get to know the main suspects. These are two of the most famous concepts in all of science: the Big Bang and the black hole. The first step is to understand them not as cartoons, but as the nuanced, complex things they really are. Let's start with the black hole. While the name is catchy, the idea is old, but it was Einstein's general theory of relativity in 1915 that gave it teeth. Einstein showed that huge objects don't just pull on things. They literally bend the fabric of reality, a 4D stage he called spacetime. What we feel as gravity is just us moving along those curves. A year later, a physicist named Karl Schwarzschild was playing with Einstein's equations and found something terrifying. He realized that if you squeeze enough stuff into a small enough space, spacetime would bend so severely that it would fold in on itself, creating a pocket from which nothing can escape. Not a star, not a planet, not even light. This point of no return is the event horizon. It's not a surface you could touch, it's a one-way door. Once you cross it, every possible path you could take leads in just one direction: inward, toward the center. Just outside this boundary, gravity is so intense it would stretch any object into a long, thin strand, a grim process physicists call spaghettification. At the heart of a classical black hole lies the singularity, a point of supposedly zero volume and infinite density, where all the matter is crushed into an impossibly small space. Here, our known laws of physics just stop working. For many physicists, the singularity isn't real, but a sign that our theories are broken. One thing to get straight is that black holes aren't cosmic vacuum cleaners. If our sun were magically swapped with a black hole of the exact same mass, Earth would keep orbiting it just fine, though it would get very, very cold. You have to get right up to the event horizon to be in danger. And they are very real. We've detected the gravitational waves from their collisions, tracked stars orbiting the supermassive black hole in our own galaxy, and even taken a direct photo of a black hole's shadow. Now for our second character, the Big Bang. The name is also a bit misleading. It wasn't a bomb going off in an empty room. It was the beginning of space itself expanding everywhere. About 13.8 billion years ago, all the energy and space in our universe was in an incredibly hot, dense state. From that moment, the universe started expanding and cooling. In the very first fraction of a second, it went through a burst of insane expansion called cosmic inflation, where space itself grew faster than the speed of light. As it cooled, particles formed, then atomic nuclei. After about 380,000 years, the universe cooled enough to become transparent, letting light travel freely. The faint afterglow of that moment is still visible today as the cosmic microwave background, or CMBA baby picture of our universe. Over billions of years, gravity pulled matter together to form the vast web of galaxies we see today. The Big Bang Theory is a huge success, but it leaves some big questions open. What started it? What came before? The theory tells us how our universe grew, but it's totally silent on the why. So, there are our two players. A black hole, a cosmic prison leading to a point where physics breaks, and the Big Bang, our universe's origin story. On the surface, they seem like total opposites. But what if they're two sides of the same coin? The investigation starts with a clue that feels a little too perfect to be an accident. The first clue, a cosmic coincidence. Every good detective story has that moment where a piece of evidence turns the whole case on its head. For us, that moment comes from a simple calculation that connects the scale of our entire universe to the physics of a single black hole. First, we need to define the observable universe. This isn't the asterisk hole universe, which might be infinite. It's just the part we can see a sphere around us whose edge is the farthest distance light has had time to travel since the Big Bang. That edge is now about 46.5 billion light-years away. This is our cosmic horizon. Physicists can estimate the total mass and energy within this sphere. It's an astronomical number, but it's calculable. Now, remember the Schwarzschild radius? It's the formula that tells you how big a black hole's event horizon is for a certain amount of mass. The Sun's Schwarzschild radius is about 3 kilometers. Earth's is the size of a marble. The formula is simple. More mass equals a bigger radius. So, what happens when you take the estimated mass of our entire observable universe and plug it into that black hole equation? What would be the size of a black hole that contained everything? When physicists first did this, they were floored. The Schwarzschild radius for a black hole with the mass of our universe was almost exactly the same as the measured radius of our observable universe. Think about that for a second. The equation that defines the size of a black hole, when you feed it the mass of our universe, spits out the size of our universe. The average density of everything spread across billions of light-years is just right to put our cosmic horizon exactly where an event horizon would be for a black hole of the same mass. Is this just a fluke? A meaningless coincidence of our current era? Many think so. But in cosmology, when numbers line up this perfectly, it's often a hint that there's a deeper connection we're missing. It's like finding a random key on the street, trying it on your front door just for fun, and discovering it fits perfectly. You could dismiss it as a 1 in a billion chance. Or, you could start wondering if that key was made for your lock all along. This size coincidence is our first big clue. It makes us ask the central question. Could the edge of our observable world and a black hole's event horizon be the same thing, just viewed from two different perspectives? Suddenly, the idea that we're living inside a black hole starts to sound less like fiction and more like something the math itself is pointing to. The second clue, the horizon problem 2.0. The first clue was a startling coincidence. The second clue takes us deeper, into one of the biggest puzzles in cosmology, involving that baby picture of our universe, the cosmic microwave background. The original, horizon problem, is a classic conundrum. When we look at the CMB, we see that it's astonishingly uniform in temperature, about 2.7 Kelvin in every direction. The patch of sky over here is the same temperature as the patch on the complete opposite side, to an accuracy of 1 part in 100,000. This is a problem. When that light was first emitted, those two opposite regions of the sky were already millions of light-years apart. There just hasn't been enough time in the history of the universe for them to have ever been in contact. Light couldn't have traveled between them to even out their temperatures. It's like finding two people on opposite sides of the planet who've never met or spoken, but are wearing the exact same custom-tailored outfit. How did they coordinate? The mainstream solution is cosmic inflation, that hyper-fast expansion in the first moments of time. Inflation proposes that these regions were once close enough to sync up their temperatures, and then were suddenly ripped apart to opposite ends of the universe. It's a powerful and elegant fix. But the black hole universe theory offers a different perspective. It asks us to rethink the boundary itself. As we've established, our universe has a cosmic horizon, a boundary in time, beyond which we can't see. A black hole has an event horizon, a boundary in space, beyond which nothing can escape. From our perspective inside, the cosmic horizon is in our past. We see the light from the Big Bang coming from it in all directions. For an observer outside this structure, in a parent universe, the event horizon is in their future. It's a place they can see things fall into, but never see what happens on the other side. The theory proposes that these two horizons are the same thing. Our cosmic horizon is a black hole's event horizon, just perceived differently from the inside. This changes everything. The Big Bang wasn't a singularity in our past. Instead, the formation of a black hole in a parent universe was our beginning. What an outside observer sees as matter collapsing into a black hole, we, on the inside, experience as the Big Bang, an expansion outward from a hot, dense state. The arrow of time in our universe could be a direct result of being inside an event horizon, where all motion is forced in one direction. Inward, away from the boundary. This gives a new angle on the horizon problem. In some of these models, like those from physicist Nikodym Poplavsky, the matter collapsing to form the black hole doesn't hit a singularity. Instead, thanks to a quantum twisting force called torsion, it bounces. This big bounce would be so energetic it would naturally create a smooth, uniform universe. The uniformity of the CMB, then, isn't a mystery. It's a direct result of the physics of its birth. The horizon we see isn't a problem to be explained away. It's the very boundary of our existence, the event horizon of our cosmic parent. The investigation deepens. A universe of fractals and echoes. Our first two clues connect our universe's size and horizons to black holes. Now we venture into the deep end, where physics starts to look like a hall of mirrors, with patterns repeating at every scale. This is the idea of a fractal, self-similar universe. A fractal is a pattern that repeats itself at different sizes. Think of a lightning bolt splitting into smaller, similar-looking branches, or the way a tree's large branches split into smaller ones, which then split into even smaller twigs. Nature seems to love this repeating logic. So, what if the universe itself is a fractal? This isn't just philosophy. The biggest struggle in physics today is connecting general relativity, the theory of the very big, with quantum mechanics, the theory of the very small. What if they aren't meant to be a single theory? What if they're just the right rulebooks for different scales of the cosmic fractal? This opens the door to a mind-blowing concept: nested realities. Some physicists, like Lee Smolin, proposed a theory of cosmological natural selection. The idea is that when a black hole forms, it creates a new baby universe inside it, where the laws of physics might be slightly different. Universes that happen to have laws that are good at making stars, and therefore lots of black holes, will have more offspring. This process would naturally select for universes like ours, which is exceptionally good at making black holes. Stack this with another radical idea: the holographic principle. Born from studying black holes, it suggests that all the information to describe a 3D volume of space can be encoded on its 2D boundary, like a hologram. If our universe is a black hole, it means our entire 3D reality could be a holographic projection of information stored on the 2D event horizon that forms the edge of our cosmos. This paints a picture of infinite, nested Russian dolls. Our universe is inside a black hole in a parent universe. Our reality is a hologram projected from its boundary. Inside our universe, we see billions of other black holes, and each one could contain another universe, another hologram, another level down in the fractal. And so on, forever. This sounds untestable, but there might be a clue. Physicist Nikodym Poplavsky predicted that if we were born inside a spinning black hole, that spin would be imprinted on our universe, creating a preferred direction or cosmic axis. For decades, we've assumed the universe looks the same in all directions. But some recent observations are challenging this. A few studies have found tantalizing hints of a cosmic alignment. One analysis of hundreds of thousands of galaxies suggested a slight but statistically significant bias in the direction they spin. These findings are highly controversial and very preliminary. Scientists are actively debating whether this is a real signal or just an error in our measurements, perhaps caused by our own galaxy's rotation. But if this cosmic spin is ever confirmed, it would be powerful evidence that our universe was born with a rotation exactly what you'd expect if you were born inside a spinning black hole. We've just journeyed to the absolute edge of physics, where universes might be nested inside each other like cosmic dolls. If your mind is racing right now, and you love exploring these kinds of reality-bending ideas, this is a great time to subscribe to the channel. We dive into cosmic mysteries like this every week, and you won't want to miss what's next. The reality check. The case against. We've built a compelling case. But a good investigation has to challenge its own assumptions. It's time to hear the scientific arguments against the idea that our universe is a black hole. First, and most importantly, is the nature of the singularity. In a standard black hole, the singularity is a point asterisk in space asterisk a location at the center you fall toward. But the Big Bang singularity was a moment in time. It happened everywhere at once. This is a fundamental, conceptual difference in the geometry of the two phenomena. While newer models propose a bounce instead of a singularity, the classical comparison remains a major hurdle for many physicists. The second objection targets the very calculation that started all this. That neat coincidence between our universe's radius and its Schwarzschild radius? Many physicists argue it's a flawed comparison. The Schwarzschild formula is for a simple, static black hole in an empty void. Our universe is dynamic, expanding, and filled with stuff everywhere. Using that formula for the whole cosmos is like comparing apples and oranges. The fact that the numbers line up today might just be a temporary fluke. Third, that evidence for a rotating universe is shaky, at best. The signals are incredibly faint, and there are many ways systematic errors could create the illusion of a pattern. Most scientists prefer the simpler, established model of an even and uniform universe, which explains our observations remarkably well without needing exotic new ideas. Until the evidence for cosmic rotation is overwhelming, it remains a curious anomaly, not proof. Finally, there's the issue of what's on the outside. If we are in a black hole, it must exist in a parent universe that we can never observe or test. The theory solves our origin by pushing the problem up a level, creating an endless chain of untestable causes. Science relies on testable predictions, and a parent universe is, by definition, beyond our reach. This is why the black hole universe theory, for all its beauty, is still a fringe idea in cosmology. It's not the consensus view. The clues are intriguing, but the counter-arguments are strong, and the jury is still very much out. The verdict? A universe of wonder. So, where does that leave us? We've followed the trail, from a stunning mathematical coincidence to the dizzying idea of a fractal cosmos, and we've faced the sober scientific reality check. Is our universe inside a black hole? The honest answer is, we don't know. And it's important to be clear that this is not the accepted theory of cosmology. The standard Big Bang model, with inflation and dark energy, is still the most successful explanation we have for the universe we see. But this hypothesis is more than just a fantasy. It's a powerful thought experiment. It's a way for physicists to probe the limits of our theories and imagine what else could be possible. Ideas that start on the fringe sometimes move to the center. General relativity itself was once a radical departure from the norm. The real value of this theory might not be whether it's literally true, but in the questions it forces us to ask. It connects the largest things in the universe to the smallest. It links the death of a star in one reality to the birth of a cosmos in another. It offers potential, if speculative, answers to some of the most stubborn problems in physics, from what started the Big Bang to the one-way nature of time. It fundamentally reframes our perspective. The black hole is no longer just a destroyer. It's a potential creator, a cosmic womb for new worlds. It suggests the universe may not have had a single beginning, but is part of an eternal cycle of birth and rebirth. Our existence could be just one chapter in an infinite story, a single layer in an endless cosmic fractal. And maybe that's the real point. Whether we live in a black hole or not, the fact that we can even ask these questions is a testament to the power of human curiosity. It's a reminder that what we know is just a snapshot of a much larger reality that is still unfolding. The next time you look up at the night sky, remember the mystery. We are a part of the cosmos that has woken up and is trying to understand itself. And the clues are everywhere. The answer to the ultimate question, where did all of this come from, might just be hiding in the shadows of those silent, beautiful, and terrifying black holes. The investigation continues. Geometry proves our reality is a shadow. Take a good look at the world around you. Feel the weight of the object in your hand, the solid floor beneath your feet, the three-dimensional space you move through. It all feels so real. It feels like the fundamental, bedrock truth of existence. But what if I told you that everything you're seeing, everything you're feeling, is a shadow? I don't mean that as a metaphor or some philosophical thought experiment. I mean it as a literal, geometric projection, cast from a higher, unseen reality. We all get how a shadow works. A three-dimensional object blocks a light source and casts a flat, distorted, two-dimensional echo of itself onto a surface. The information gets compressed, warped, and is ultimately incomplete. The shadow isn't the object itself, just a lower-dimensional whisper of it. Now, let's take a wild leap. What if our entire three-dimensional world is the shadow? What if the reality you inhabit is just a complex and convincing projection of another reality with more dimensions than we can possibly perceive? This isn't just science fiction. It's a profound possibility hinted at by the universe's most fundamental language, geometry. The clues aren't hidden in exotic particles or distant galaxies, but in the very fabric of space and time you occupy right now. The way your reality is shaped, the way it curves and bends, might just be the biggest geometric hint that our world is a shadow, and we are simply figures moving within it. The world you see around you might be a shadow. And the clues for this incredible idea lie in the elegant language of geometry. Think about it. Just as a shadow is a warped, flat projection of a 3D object, our 3D world could be a shadow of a deeper, higher dimensional reality. The evidence isn't in some far-off physics lab, but in spacetime itself. For over a century, we've known that the fabric of our universe is curved by gravity. This isn't some cosmic mistake, it's a fundamental feature. And it's a giant geometric clue. Imagine a heavy bowling ball warping a stretched trampoline. Now picture our whole universe as that sheet curved by the mass of stars and galaxies. What if that warp is hinting at something bigger? That we're not just floating in flat, empty space, but living on the surface of a higher dimensional structure? Stick with me. Today, we're exploring the mind-bending idea that our 3D world, plus time, might be just one layer embedded in a space with extra dimensions, like a hologram projected from a deeper reality. We'll unpack the physical hints from geometry, especially spacetime curvature, why it suggests the asterisk possibility of being embedded in something more, and what that would mean. This is all about the juicy ideas that keep physicists up at night. By the end, you'll see why this isn't just sci-fi. It's geometry whispering some incredible secrets about the nature of reality. The core analogy: the shadow on an uneven surface. Before we get into the heavy stuff, let's ground ourselves in this one core analogy. Getting this intuitively is the key to the whole concept. Picture a dark room with a single, bright light. You hold up your hand. On a flat wall, a clean, two-dimensional silhouette appears. It has height and width, but no depth. All the rich, 3D information of your hand, its texture, its volume is flattened into a simple dark shape. An observer who could only see this 2D wall would have a very limited idea of the 3D object casting the shadow. Now, let's change one thing. Instead of a flat wall, the shadow falls on a crumpled piece of paper or a wrinkled bedsheet. What happens to your hand's shadow? It's no longer a clean silhouette. It's warped. Stretched in one spot, compressed in another. The smooth outline becomes a jagged, unpredictable shape, dictated entirely by the bumps and folds of the surface it's on. An observer living in this 2D world, on the surface of that crumpled paper, would experience a bizarre reality. If they tried to measure things, they'd find that their geometry is all wrong. What should be straight lines would appear to bend. Distances would seem to shrink and expand randomly. The rules of flat geometry just wouldn't work. If this 2D observer were a scientist, they might invent all sorts of complex forces and fields to explain these distortions. But the real answer wouldn't be found in their 2D world at all. The answer is that their entire reality is a projection on a curved surface. The distortions aren't a property of the shadow. They're a property of the space the shadow lives in. That curvature is the biggest clue they could find that their world isn't the whole story. This is the heart of the argument. For over a century, since Einstein's theory of general relativity, we have known with incredible precision that our universe is like that uneven surface. The 3 dimensions of space and the 1 dimension of time are woven into a 4-dimensional fabric, spacetime. And this fabric isn't flat. It's curved and warped by mass and energy. A star doesn't pull a planet with some invisible rope. The star's mass creates a deep dip in spacetime, like that bowling ball on the trampoline, and the planet is just rolling along the straightest possible path through that curved space. This curvature isn't just a theory, it's a measured and confirmed fact. We see it in how light from distant stars bends around massive galaxies, an effect called gravitational lensing. We measure it in our GPS satellites, which have to constantly correct for the fact that time literally flows slower closer to Earth's gravity. The Gravity Probe B satellite even measured how Earth drags the fabric of spacetime around with it as it spins. The world we live in is not a flat, predictable stage. It is a dynamic, curved, and warped landscape. And just like the distorted shadow on the crumpled paper, this very curvature is the giant, waving red flag, the geometric hint that our reality might not be the fundamental one. The laws of our universe might just be the strange geometry of a shadow, cast on the uneven fabric of the cosmos. The scientific foundation whispers of a deeper code. Okay, so our universe is curved. That's a cool fact, but how do we get from a curved reality to a projected one? This isn't just a philosophical guess. It's a move inspired by some of the most profound ideas in modern physics, which started with a puzzle about black holes. The idea is called the holographic principle. It all began when physicists wondered, when a black hole swallows a star, what happens to the information that made up that star? Quantum mechanics has a strict rule. Information can never be destroyed. But a black hole was thought to be a one-way street. So where did the information go? In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered something startling. They found that the amount of information a black hole can hold is not proportional to its 3-dimensional volume, as you'd expect. It's proportional to the 2-dimensional area of its event horizon, its surface of no return. This was a bombshell. It was as if all the information about everything that ever fell into a giant library wasn't stored on the shelves inside, but was somehow encoded on the building's outer walls. This led physicists Gerard T. Hooft and Leonard Susskind to propose something even bolder: the holographic principle. They suggested this might not just apply to black holes, but to the entire universe. The idea is that the physics of a volume of space could be completely described by a different set of laws written on a lower dimensional boundary of that space. Our 3D reality, in this view, could be a holographic projection of information stored on a distant 2D surface. This sounds wild, but it got a huge boost in 1997 from physicist Juan Maldacena. He discovered a precise mathematical link, a kind of dictionary, called the ADS-CFT correspondence. On one side of the dictionary, you have a theory with gravity in a specific, negatively curved, five-dimensional spacetime, anti-de Sitter space, or ADS. On the other side, you have a quantum theory without gravity, living on the flat, four-dimensional boundary of that space, a conformal field theory, or CFT. Maldacena showed that these two theories are completely equivalent, they are dual to each other. Anything that happens in the 5D world with gravity has a matching description in the 4D world without gravity on its boundary. It was the first concrete, mathematical example of the holographic principle in action. It proved that a higher dimensional reality with gravity could, in principle, be fully encoded by a lower dimensional system. Now, it's really important to be clear here. Our universe is not an anti-de Sitter space. Our universe is expanding and has a different kind of curvature. So, the ADS-CFT correspondence doesn't directly describe our reality. However, its discovery was a monumental shift. It showed that the idea of a holographic universe wasn't just speculation, it was mathematically plausible. The principle was sound. It provided a theoretical playground proving that the universe could work this way. So we have two big ideas on the table. First, the analogy. A curved, distorted space could be a hint that it's a projection. Second, a theoretical framework from physics. The holographic principle, which says our reality could be a projection. The next question is, does our universe's geometry fit the description? The revelation, geometry is the hint. This is where the threads come together. We started with the idea of a shadow on an uneven surface. We explored a scientific basis for it with the holographic principle. Now, we ask, does the specific, measured geometry of our curved spacetime behave in a way that makes sense if it were a projection from a higher dimension? The clues are compelling. When physicists talk about curvature, they mean intrinsic curvature. This is something you can measure from within a surface. An ant on a sphere can tell its world is curved without ever leaving it by drawing a big triangle and finding its angles add up to more than 180 degrees. This is the curvature Einstein described in general relativity, which we can measure from inside our 4D spacetime. But there's also extrinsic curvature, which is how a surface bends within a higher dimensional space. A flat sheet of paper has no intrinsic curvature. But you can roll it into a cylinder. The cylinder is still intrinsically flat. A triangle's angles are still 180 degrees, but it clearly has extrinsic curvature in our 3D space. For a long time, spacetime's curvature was treated as purely intrinsic. But could our curved 4D spacetime be embedded in a larger, flat, higher dimensional space, just like a curved 2D sphere is embedded in flat 3D space? A stunning piece of math called the Nash embedding theorem says yes. John Nash proved that any curved space, including our spacetime, can, in principle, be mathematically described as if it were embedded in a higher dimensional flat space. This is a mathematical guarantee. It doesn't prove extra dimensions are real, but it shows it's a valid way to think about our universe's geometry. The more complex and twisted the curves of a space are, the more extra dimensions this mathematical embedding might require. This leads us to a speculative but exciting idea in physics: brane world cosmology. Inspired by string theory, these models propose that our entire 4D universe is a brane, like a membrane floating in a higher dimensional reality called the bulk. In this picture, most particles and forces, like electromagnetism, are stuck to our brane. But gravity, these theories suggest, is different. Because gravity is the geometry of spacetime, it might not be confined to the brane. It could leak into the bulk. This offers a potential, and very elegant, explanation for one of physics' biggest mysteries. Why is gravity so much weaker than other forces? Perhaps we only feel a fraction of its true strength because most of it is diluted across those unseen extra dimensions. In this view, the curvature we feel as gravity is the tangible effect of the bulk on our brane. The search for these extra dimensions is active. At the Large Hadron Collider, LHC, physicists have looked for clues, like energy seemingly vanishing from a collision if a particle were to escape into the bulk, or tiny black holes forming at lower energies than expected. So far, no definitive evidence has been found, but every new experiment refines the search. So let's put it all together. Our reality is geometrically curved. We call it gravity. Mathematics guarantees that such a curved space can be viewed as a surface within a higher dimensional flat space. And speculative theories like the holographic principle and brane cosmology provide a physical framework for how that might work. The weakness of gravity and the complex geometry of spacetime are tantalizing hints. The distortion of the shadow is the clue to the object casting it. The curvature of our reality might just be the geometric whisper that it's a shadow of something far grander. We've journeyed from a simple shadow to the cutting edge of theoretical physics. We've seen how the very shape of our universe might point towards a possibility almost too big to wrap your head around. If you find this stuff as fascinating as I do, and you want to keep questioning the nature of reality, consider subscribing to the channel. We explore these cosmic questions every week. And let us know in the comments. What do you think? Is the curvature of spacetime just a property of our universe, or does this geometric argument convince you there might be more to it? We love reading your perspectives. So, where does this leave us? We're standing on a cliff, looking at two very different pictures of our existence. In one view, the universe is exactly what it seems. 4 dimensions, 3 of space, 1 of time, curved by matter and energy. The curvature is just a property of our universe, and that's the end of the story. It is the object, not the shadow. This is the standard view, and it works perfectly well to describe what we observe without needing any new, unproven physics. In the other view, the one we've explored today, our universe is a kind of illusion, a beautiful and convincing one, but an illusion nonetheless. A shadow. A projection. A membrane adrift in a higher dimensional ocean. In this picture, the fundamental laws of reality exist in a place we can't access, and what we call physics is just the warped echo of those deeper laws playing out on the curved surface of our spacetime brane. The solid world would be, in a sense, a complex pattern of information. The evidence, as we've seen, is geometric. It starts with the simple, measured fact that our universe is not flat. This curvature is the master clue. When you combine that with the theoretical power of ideas like the holographic principle and brane world models, a compelling story starts to form. The weakness of gravity, the mathematical possibility of embedding, the potential for a holographic description, all these pieces fit together to paint a picture of our reality as a small part of a much larger cosmos. We don't have the final answer. Experiments at places like the LHC haven't yet found the smoking gun for extra dimensions they were hoping for. But science progresses by ruling things out. And future observations, perhaps from new gravitational wave detectors, could reveal anomalies that only make sense if gravity is interacting with dimensions beyond our own. The high luminosity LHC, set to begin operations in the coming years, will offer unprecedented precision to search for these new phenomena. This idea really transforms how we see the universe. It suggests that the answers to our deepest questions might not be found by looking deeper within our world, but by searching for hints of the world beyond it. We are like those 2D scientists on the crumpled paper, slowly realizing that the strange warps in their world are caused by a third dimension they can't even see. So, the next time you feel the pull of gravity, that gentle force anchoring you to the earth, take a second. Remember what it is. the curvature of spacetime. And ask yourself, what's causing that curve? Is it just the mass of the Earth in our 4D world? Or are you feeling the faint, distant echo of a higher reality, pressing down on the fabric of our own? Are you feeling the geometry that hints our world is a shadow? The search for that answer is the greatest detective story of all time. Your mass is an illusion from a hidden dimension. You feel solid, right? Real. The chair you're sitting on, the phone in your hand, the very bones in your body, they all have substance, they have weight. We call this mass. For decades, science has had a tidy, Nobel Prize-winning story for where mass comes from. But what if that story, as successful as it is just a shadow of a much deeper, much weirder truth? What if I told you that the very stuff you're made of, your solidity, your mass, is an illusion? A trick of the light, cast from a hidden dimension you can never see or touch, but that dictates the very nature of your existence. The story of your mass isn't just about some cosmic field. It's a story that suggests your physical reality is a projection and echo of an unseen geometry. The comfortable reality, the standard story of mass. To see how reality might be an illusion, first we need to get a handle on the story we've been telling ourselves for the last 50 years or so. It's called the Standard Model of Particle Physics. Think of it as our best, most detailed map of the subatomic world. It lists every fundamental particle we've ever found, from the electrons powering your screen to the quarks that build the atoms in your body. And it describes 3 of the 4 fundamental forces that boss them around: electromagnetism and the strong and weak nuclear forces. It is, no exaggeration, the most successful scientific theory in human history, tested and confirmed to an insane degree of precision. But for a long time, this beautiful map had a giant hole in it. The math of the Standard Model worked perfectly, but with one little catch: all the fundamental particles had to be massless. This was a huge problem. We knew particles had mass. We could measure it. An electron has a tiny mass, but a top quark is a monster by comparison, about 347,000 times more massive. If the theory demanded they have zero mass, then the theory was just plain wrong. It was like having a perfect world map where all the mountains are shown as being at sea level. Then, in the 1960s, a group of physicists, including Peter Higgs, came up with a jaw-droppingly elegant fix. They proposed that the entire universe, every last cubic millimeter of space from the core of the sun to the void between galaxies, is soaked in an invisible energy field. We now call it the Higgs field. The best analogy for this is a classic for a reason. Imagine you're at a massive, packed party in a huge ballroom. The crowd of people is the Higgs field, spread out everywhere. Now, someone not very famous walks in. They can move through the room pretty easily, with people barely noticing. That's like a particle with very little mass, such as a photon, the particle of light. It doesn't really interact with the Higgs field, so it zips along at the fastest speed possible, the speed of light, and has zero mass. But now, imagine a huge celebrity walks into that same room. The second they step onto the floor, they're mobbed. A cluster of fans and photographers immediately forms around them. Their movement is totally bogged down. It's hard for them to speed up, and it's hard to slow down. They've gained a kind of inertia from interacting with the crowd. From the outside, it just looks like they've become heavy. This is exactly how the Higgs mechanism works. Particles aren't just born with mass. They get it by interacting with the Higgs field. A particle like an electron only interacts a little, so it gets a little mass. A top quark interacts a lot, gathering a huge cluster of the field around itself, which makes it incredibly massive. Your body is made of atoms, which are made of protons, and neutrons, which are made of quarks. Those quarks are constantly wading through this cosmic Higgs field, and it's that resistance, that drag, that we perceive as their mass. And by extension, your mass. For decades, this was just a brilliant theory. It patched the hole in the Standard Model and gave a beautiful explanation for mass. But that's all, it was a theory. The final proof landed on July 4, 2012. Scientists at CERN's Large Hadron Collider, the most complex machine ever built, announced they had finally found the particle associated with the field. They had detected the Higgs boson. It was the cluster of people. In our analogy, a real ripple in the field, proving the field was real. It was a massive victory, the final piece of the Standard Model puzzle, and it won Peter Higgs and François Englert the Nobel Prize in Physics. The story, it seemed, was complete. Mass comes from the Higgs field. End of story. Except, in physics, the end of one story is almost always the beginning of a much deeper mystery. The agitation. Cracks in the foundation. A successful theory isn't the same as a complete theory. Newton's theory of gravity was wildly successful. It could predict the orbits of planets and the path of a cannonball. It just worked. But it couldn't explain weird little things, like the orbit of Mercury. It took Einstein's general relativity, a deeper and more complete theory, to solve that puzzle and show that Newton's law was really just an approximation. Today, the Standard Model and the Higgs mechanism are in a similar spot. They work beautifully, but they leave us with some profound puzzles that point to a reality far stranger than the model suggests. The biggest, most glaring of these is a cosmic mismatch so huge it's been called the hierarchy problem. The problem is this. Why is gravity so ridiculously, absurdly weak? You might not think of gravity as weak. It sticks you to the Earth and holds galaxies together. But compared to the other forces, it's a total pushover. Think about it. You can pick up a paperclip with a tiny fridge magnet. That magnet's electromagnetic force is overpowering the gravitational pull of the asterisk entire planet Earth. The whole mass of a 6 trillion kilogram planet is being beaten by a dinky piece of magnetized metal. In particle physics, this isn't just a fun fact, it's a theoretical disaster. The forces in the Standard Model operate at a certain energy level, the electroweak scale. Gravity seems to play in a completely different ballpark, the Planck scale, which is about a quadrillion times higher in energy. That's a 1 with 16 zeros after it. This is where the Higgs boson comes back to haunt us. The Higgs's mass, which we measured at the LHC, is pretty light, around 125 giga-electron volts. According to quantum mechanics, this mass shouldn't be stable. The quantum world is a buzzing, fizzing foam of virtual particles popping in and out of existence. These virtual particles should interact with the Higgs, and their combined energy should drag its mass all the way up to that crazy high Planck scale. For the Higgs to be as light as we see it, all of these enormous quantum effects must cancel each other out with a precision of about 1 part in 10,000 trillion. It's like having two people who each owe you $1 quadrillion, and when they pay you back, the difference is a single penny. It's not impossible, but it feels like a ridiculously lucky coincidence. Physicists call this a fine-tuning problem. It suggests our theory is missing something fundamental that naturally explains why the Higgs is so light and gravity is so weak. We haven't found a deep principle, we've just plugged in a number that looks like it's been dialed in by hand with almost impossible precision. And this isn't the only crack in the foundation. The Standard Model, for all its glory, says nothing about gravity. It doesn't explain dark matter, the invisible stuff making up about 27% of the universe. Nor does it explain dark energy, the mysterious force making up another 68% that's causing the universe to expand faster and faster. Our triumphant Standard Model, the theory that explains your mass, only describes about 5% of the known universe. So while the Higgs field tells us how particles get mass, it doesn't explain why the field itself has these bizarre, fine-tuned properties. It doesn't explain itself. Just like with Newton's gravity, we have a theory that works, but it's screaming at us that there's a deeper reality waiting to be discovered. And to find it, we might have to look in places we never thought to look. A radical solution: the idea of extra dimensions. So, if our best theory has these massive holes in it, where do we even start looking for answers? Well, one of the most mind-bending ideas in all of physics doesn't just add a new particle or force. It suggests the very stage of reality spacetime itself is bigger than we thought. It proposes we're living in a universe with hidden dimensions. This idea isn't even new. It goes back to the 1920s, right after Einstein's general relativity had redefined gravity as the curvature of four-dimensional spacetime. A Polish physicist named Theodor Kaluza had a wild thought. What if there's a fifth dimension? He showed Einstein that if you take the equations of general relativity and just add one more dimension of space, something amazing happens. Out pop the normal equations for gravity in 4 dimensions, but you also get a second set of equations that perfectly matched the theory of electromagnetism. It was an incredible idea. 2 fundamental forces, gravity and electromagnetism, could be one and the same, just by adding an extra, unseen dimension. But that raises an obvious question. If it's real, where is it? We can move forward, backward, left, right, up, down. Where's the other direction? A few years later, a Swedish physicist named Oscar Klein came up with a brilliant answer. The fifth dimension is compactified. It's curled up into a tiny circle, so small we can never see it or move in it. The classic analogy here is a garden hose. From far away, it looks like a one-dimensional line. But if you were a tiny ant on the hose, you'd know it has 2 dimensions. You can walk along the length, but you can also walk around its circumference. Klein suggested that at every single point in our 3D space, there's a tiny, curled-up circle of a 4th spatial dimension, just too small for us to notice. This Kaluza-Klein theory was beautiful, but it was incomplete and eventually fell out of fashion. But the idea of extra dimensions never really died. It was brought back to life in a much bigger, bolder framework: string theory. String theory is a leading candidate for a theory of everything. It says the fundamental bits of reality aren't particles, but tiny, vibrating strings. Like a guitar string playing different notes, these fundamental strings can vibrate in different patterns. A string vibrating one way looks like an electron. A different vibration looks like a photon. Another, a quark. All the particles and forces are just different notes of these strings. But for the math to work, string theory requires something extraordinary. Not 3 or 4 spatial dimensions, but maybe 10 or 11 spacetime dimensions in total. That means on top of our 3 big dimensions, there must be 6 or 7 extra ones, all curled up into fantastically complex shapes. This opens up a stunning new way to solve the hierarchy problem. In the 90s, physicists proposed that our entire 3D universe is just a brane, like a membrane floating in a higher dimensional space called the bulk. In this model, all the standard model particles and forces, you, me, light, everything are stuck to this brane. We're like water droplets that can only slide around on the surface of a shower curtain, unable to get into the rest of the bathroom. But there's one exception: gravity. Gravity, being the geometry of spacetime itself, isn't stuck to the brane. It's free to spread out into the entire higher dimensional bulk. This gives a shockingly simple explanation for why gravity seems so weak. It's not actually weak. It's just as strong as the other forces, but its influence gets diluted as it leaks out into these extra dimensions. We, living on our brane, only feel a tiny fraction of its true strength. Now, let's be clear. This isn't just sci-fi. These are testable ideas. If these extra dimensions exist and are large enough, the Large Hadron Collider could smash particles together with so much energy that some of it, maybe in the form of a graviton particle, gets knocked off our brane and leaks into the bulk. We'd see that as energy just vanishing from our detectors. So what have the experiments found? So far, nothing. The LHC has seen no definitive evidence of energy leaking away. Tests of gravity at very small distances have also come up empty. This means the simplest versions of these large extra dimension models have been ruled out. But it doesn't kill the idea. It just means that if extra dimensions exist, they're smaller or more complex than we'd hoped. The search continues, but it's clear the answers might not be found in our 3 dimensions alone. Mass from geometry, the deepest illusion. The idea that gravity might be diluted by extra dimensions is already mind-bending. But what if their role is even more fundamental? What if hidden dimensions don't just explain weak gravity, but also create the properties of particles themselves? This is where we get to the core idea. Your mass is an illusion, generated by the geometry of an unseen world. To get this, we have to go back to Einstein's biggest lesson. Gravity isn't a force. It's a consequence of the curvature of spacetime. The sun doesn't pull the Earth. It warps spacetime around it, and the Earth follows that curve. Physics, Einstein showed, is geometry. Now let's apply that lesson to the extra dimensions of string theory. If particles are vibrating strings, and those strings are wiggling around in a 10-dimensional spacetime, then the geometry of those tiny, curled-up dimensions is everything. The way a string can vibrate depends on the shape of the space it's in. A short guitar string makes a higher note than a long one. A string vibrating in a tiny, cramped space can only have certain vibrational patterns. This is the key. In these theories, a particle's properties, its charge, its spin, its mass are all determined by how its string vibrates. And those vibrations are dictated by the geometry of the hidden dimensions. So where does mass come from in this picture? A particle's mass in our 3D world could simply be a reflection of its energy from vibrating and moving through the hidden dimensions. Let's try an analogy. Imagine a bead on a tiny, circular wire loop. You can't see the loop, it's a hidden dimension. All you see is the bead. Now, someone flicks the bead so it starts spinning around the loop. From your limited point of view, it's not going left or right, it's just sitting there. But you know it has energy, the kinetic energy of its motion around that hidden circle. And thanks to Einstein's E equals mc squared, energy and mass are 2 sides of the same coin. The energy the bead has from moving in that hidden dimension would show up in your world as mass. The faster it spins in the unseen circle, the more energy it has, and the more massive it appears to be. This is the radical proposal. Mass isn't something a particle has. It's a measure of a particle's vibrational energy as it jiggles through geometric hallways that are totally invisible to us. The different masses of particles, from the feather light electron to the super heavy top quark, would just correspond to the different notes or vibrational modes they can have in the specific, complex shape of the hidden dimensions. The laws of particle physics become a symphony played on a microscopic, 6-dimensional instrument. Your mass, that feeling of solidity, is a projection. A shadow cast from a higher dimensional reality. The stuff you're made of is just the hum of countless strings, with their vibrations echoing out of those unseen dimensions and being felt in our world as mass. So what about the Higgs field, the Nobel-winning discovery? This idea doesn't necessarily replace it. It could be the deeper explanation for it. The Higgs field could be what's called an effective theory, our simplified, 3D description of this much richer, higher dimensional reality. The geometry would be the cause, and the Higgs field would be the effect we measure. Exploring these ideas is what science is all about. It's about pushing our best theories to the breaking point and asking, what if? Until we uncover the next layer of reality. These concepts are right at the frontier of human knowledge, a mix of proven science and bold, informed speculation. If you love having your mind stretched and your reality put into question, if you want to keep digging into the biggest questions out there, then think about subscribing. We're on a journey to understand everything from the origin of the universe to the nature of consciousness, and we'd love for you to come along for the ride. Click that subscribe button and hit the bell so you don't miss what's next. The implications and the grand unknown. If we take this idea seriously for a moment, the implications are just staggering. It completely reframes our place in the cosmos. If the properties of our universe, like particle masses, are set by the geometry of hidden dimensions, a question immediately pops up. Could that geometry have been different? This leads to one of the most fascinating and controversial ideas in modern physics: the string theory landscape. The math of string theory doesn't seem to predict one single shape for the extra dimensions. Instead, it allows for a ridiculous number of possible solutions, maybe 10 to the power of 500. A1 with 500 zeros. Each solution would be a different shape for the extra dimensions, and each shape would cause strings to vibrate differently. That would result in a universe with its own unique set of particles, its own physical constants, and its own laws of physics. This is the basis for the multiverse. Our universe, with its specific particle masses that allow for stars and life, might be just one bubble in a vast cosmic foam of other universes. In another universe, the hidden dimensions might be shaped differently, resulting in a heavier electron or a massless quark, leading to a universe with bizarre chemistry, or maybe no structures at all. What we call the laws of physics might not be rigid, universal truths. They might just be the local bylaws of our cosmic neighborhood, a random outcome of how our patch of spacetime happened to cool and curl up after the Big Bang. This would be a convenient, if unsettling, solution to the fine-tuning problem with so many universes. It's no surprise we find ourselves in one where the constants are just right for us to exist. We just got lucky. Now, I have to be super clear here. This is all highly speculative. We have no direct experimental evidence for string theory, for extra dimensions, or for a multiverse. These ideas live at the extreme edge of theoretical physics, born from math and a desire for a unified theory. They are beautiful and compelling, and they solve some deep puzzles on paper, but they are not proven. Physicists are actively looking for indirect clues, but for now, this grand, geometric vision of reality remains a tantalizing dream. We started with a simple question: where does your mass come from? We traveled from the comfortable, established world of the Higgs field, a cosmic sea that gives substance to the particles making up our world. But we found deep cracks in that foundation. Puzzles like the hierarchy problem that tell us this story can't be the whole story. Our search for answers took us into the truly strange, into the speculative realm of hidden dimensions, where our entire universe could be a mere membrane in a larger cosmos. And there, we found a radical new possibility. A vision where the laws of physics are written in the language of geometry. Where particles are notes in a cosmic symphony, and where mass itself is not fundamental, but an illusion. An echo of energy, from vibrations in dimensions we can never, ever see. So, your mass hasn't vanished. The chair you're on is still solid. But the source of that solidity might be infinitely more elegant and strange than we ever imagined. It may not be something you have, but something you are, a pattern, a vibration, a complex dance unfolding across the unseen architecture of spacetime. The next time you feel the weight of your own body, or push against a solid object, take a moment. You might not just be feeling stuff. You might be feeling the resistance of a hidden geometry, a ghost of a higher dimension. You may not be a solid object living in space. You may be a pattern woven from the very fabric of space itself, a shadow of a grander, unseen, and magnificent reality. Why scientists think we're trapped in a cosmic onion? What if our universe isn't the whole story? What if this vast, star-dusted cosmos we see is just one layer of a reality so immense, so fundamentally strange, that we're like a single microbe on a grain of sand on an infinite beach? What if it's all just one layer of a vast, cosmic onion, with hidden realities folded all around us, just out of sight? This isn't a question from science fiction. It's a question bubbling up from the absolute frontier of theoretical physics. It's a possibility a number of scientists are exploring, driven by deep and persistent cracks in our understanding of, well, everything. We're told we live in a universe of 3 spatial dimensions and 1 of time. But what if that's a profound simplification? What if, woven into the very fabric of reality, there are other directions, curled up so tightly or spread out so vastly that we simply can't perceive them? Stick with me. We're going to peel back the layers of this cosmic onion, one by one. We'll start with the world you know and move steadily outward, into realms of vibrating strings, invisible membranes, and twisted geometries that defy imagination. We'll ask the hard questions. Would time itself hold steady in such a universe? Could these hidden folds explain the greatest mysteries we face, like the phantom force that seems to be pulling our galaxies apart? By the end of this, your perspective on the world on the ground beneath your feet and the sky above your head might just be changed forever. We're going to explore why some of the most brilliant minds on the planet think we are, in a very real sense, trapped inside a cosmic onion. The first layer, our comfortable, incomplete reality. Let's begin with the first, most familiar layer. Our universe. It's the world of planets and people, of galaxies spiraling in the cosmic dark of things you can touch, see, and measure. For the last century, our map of this layer has been astonishingly successful. It's called the Standard Model of Particle Physics, and it is, without a doubt, one of the greatest intellectual achievements in human history. Think of it as the ultimate recipe book for reality. It tells us with breathtaking precision what the fundamental ingredients are: a quirky family of particles like quarks and electrons, and how they interact through a set of fundamental forces. There's electromagnetism, the force that holds atoms together and brings light to our eyes. There are the strong and weak nuclear forces, which govern the chaotic dance inside the heart of every atom. For decades, every experiment we've thrown at the Standard Model has confirmed its predictions. It is, in its domain, almost perfect. But there are shadows at the edges of this beautifully lit map. Whispers of a world beyond what the Standard Model can explain. And the loudest of these whispers is the deafening silence of gravity. Isn't that strange? Gravity, the first force we ever identified, the one that holds us to the Earth, has no place in the Standard Model's recipe book. Our best theory of gravity, Einstein's general relativity, describes it as the curvature of spacetime on the grandest scales. The Standard Model, meanwhile, describes a quantum world of tiny, frantic particles. And the two theories, our two greatest descriptions of reality, absolutely refuse to talk to each other. They're written in different mathematical languages. When you try to combine them, the equations break, spitting out nonsensical infinities. This incompatibility is the first major crack in our layer of the onion. It tells us our story is incomplete. And it's not the only problem. There's what physicists call the hierarchy problem. Why is gravity so ridiculously weak compared to the other forces? Think about it. A tiny refrigerator magnet can lift a paperclip, its small electromagnetic pull effortlessly overpowering the gravitational pull of the entire planet Earth. Fundamentally, gravity is about 10 to the power of 24 times weaker than the weak force, and even weaker compared to electromagnetism. This isn't a small difference. It's a chasm that has no good explanation in our current understanding. It's as if the universe was built with one dial turned almost all the way down to zero, and nobody knows why. Then there are the two colossal mysteries that loom over all of cosmology: dark matter and dark energy. Our observations tell us that the stuff we can see, the stars, gas, and dust, accounts for only about 5% of the cosmos. More recent data from large-scale projects like the Dark Energy Survey suggest the total matter content, visible and dark, is around 30 to 32%, with the remaining 68% being something even more bizarre: dark energy. This is a mysterious pressure in the vacuum of space that's causing the expansion of the universe to accelerate. Our best map of reality, the Standard Model, says nothing about any of this. It's like having a map of Earth that only shows small islands and labels the other 95%, here be dragons. These dragons, the failure to unite gravity, its bizarre weakness, and the existence of dark matter and dark energy are not minor details. They are fundamental clues that the reality we inhabit is not the only layer. They are the urgent, driving need to peel back the onion and see what lies beneath. Peeling back to the quantum realm. To understand the cracks in our reality, we have to journey inward. Past cities and mountains, past the molecules in the air, and into the atom itself. For a long time, we thought this was the end of the road. The very word, atom, comes from the Greek atomos, meaning uncuttable. But we learned to cut it. Inside the atom, we found a nucleus of protons and neutrons, swarmed by a cloud of electrons. But we didn't stop there. We built particle accelerators, like the Large Hadron Collider at CERN, to smash these particles together with unimaginable force. When we did, we found that even protons and neutrons weren't fundamental. They are each made of 3 even smaller particles called quarks. Here, in this subatomic zoo, we find the world of the Standard Model in full swing. Particles aren't solid little balls, but fuzzy, probabilistic clouds of potential, governed by the strange laws of quantum mechanics. Forces are carried by other particles. Photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. It's a world that is deeply weird, but also deeply consistent. The interactions, the energies, the decays, they all match the predictions of the Standard Model with stunning accuracy. Yet, even here, at the smallest scales we can directly probe, gravity remains the ghost at the feast. We can describe the quantum jitter of an electron, but we can't describe its gravitational field in the same language. The equations just fall apart. For decades, this was the state of play. Physicists had these 2 magnificent theories and a giant wall of mathematical incompatibility between them. The dominant picture of particles as infinitely small points was a big part of the problem. A new, radical idea was needed. What if we've been thinking about particles all wrong? What if they weren't points at all? What if, when you zoomed in far enough, past the quark, past anything we've ever seen, you found something else? Not a dot, but a tiny, vibrating, wriggling loop of pure energy. This idea, when it first emerged, seemed like a piece of abstract math. But it would turn out to be the key that unlocked the next layer of the onion, revealing a cosmos far stranger than anyone had dreamed. It was the birth of string theory. The string theory revolution, the first hidden layers. This is where our journey takes a sharp turn from the familiar. The idea at the heart of string theory is deceptively simple. If you could zoom in on any fundamental particle, you wouldn't find a point. You would find a minuscule, one-dimensional loop of vibrating energy. A string. Think of a violin string. By vibrating it in different ways, you can produce a whole range of different musical notes. String theory proposes the universe works the same way. A string vibrating in one pattern might appear as an electron. A different pattern would be a photon. Yet another, a quark. All the different particles are just different notes, being played on the same fundamental string. It's an idea of breathtaking elegance, unifying matter and forces. Instead of a messy zoo of particles, you have just one fundamental thing. Theorists exploring this made a stunning discovery. Among the string's vibrations was one with the exact properties of the graviton, the hypothetical quantum particle of gravity. For the first time, gravity wasn't an outsider. A quantum theory had predicted gravity. It seemed like the answer to everything. But there was a catch. A huge one. The mathematics was riddled with inconsistencies unless physicists made a radical assumption. The universe doesn't just have 3 spatial dimensions. The theory only worked if it had 9 spatial dimensions plus 1 of time, making for 10 spacetime dimensions. String theory doesn't just allow for extra dimensions, it demands them for its mathematical consistency. Suddenly, the question was, if our best hope for a unified theory needs 10 dimensions, where on Earth are the other 6? Physicists proposed 2 mind-bending possibilities. The first is that these extra dimensions are compactified, curled up on themselves, so microscopically small we can't perceive them. The classic analogy is a garden hose. From far away, it looks like a one-dimensional line. But get close, and you see it has a second, circular dimension. The theory suggests that at every single point in our space, there exists a tiny, 6-dimensional shape, a complex geometry known as a Calabi-Yau manifold, curled up far smaller than an atom. We're just too big to see them. But there's a second, even wilder possibility. What if the extra dimensions aren't small at all? What if we are the ones who are trapped? This leads us to the next layer of the onion. The strange world of branes. Brane worlds. Are we living on a wall? In the mid-1990s, string theory had another revolution. Physicists realized the theory didn't just contain one-dimensional strings, but also higher-dimensional objects they called branes, short for membranes. This led to a bold new picture, brane cosmology. The idea is this. What if our entire universe, every galaxy, every star, you and me, is confined to a giant, 3-dimensional brane? Imagine our 3D universe as a sheet of paper floating in a larger, higher-dimensional room, or the bulk. We can move freely on the paper, but we can't leave it and enter the room. Our very existence is stuck to the brane. This seemingly outlandish idea provides a stunningly elegant explanation for gravity's weakness. The forces of the standard model, electromagnetism and the nuclear forces, are described by open strings, with ends that are physically anchored to our 3D brane. Their energy is stuck here with us. But gravity is different. According to string theory, gravity is made of closed loops of string. A closed loop has no ends to get stuck. This means gravitons, the particles of gravity, aren't confined to our universe. They are free to leak out from our brane and spread throughout the entire higher-dimensional bulk. This is a profound revelation. Gravity isn't inherently weak. It's just as strong as the other forces, but we only feel a tiny fraction of its true strength because the rest of its power is diluted across the extra dimensions. It's like hearing a muffled conversation through a wall. This picture reframes our place in the cosmos. Our universe is no longer everything. It's just one layer in a potentially infinite stack. There could be other branes, other universes, floating parallel to our own, maybe just millimeters away in a higher dimension. These parallel worlds would be invisible because the light and matter that make us up are stuck to our brane. But not gravity. Gravity could be the one messenger between worlds. This is the cosmic onion in its full glory. A multiverse of layered realities, stacked together, all bound by the far-reaching influence of gravity. While this idea is a powerful area of research, it faces criticism for being difficult to test and for relying on concepts like the multiverse, which some argue is more philosophy than science. Rewriting reality. What do extra dimensions change? If we're living in a higher dimensional reality, the idea has to match what we observe. Crucially, it can't violate the law of causality, the rule that a cause must always precede its effect. Does time go sideways? The question of causality. If something could take a shortcut through a higher dimension, you could imagine receiving a signal before it was sent, creating a paradox. Fortunately, the math shows this isn't the case. Even if particles can travel in more dimensions, they are still bound by the cosmic speed limit, the speed of light within the larger, multidimensional spacetime. An effect cannot outrun its cause. The arrow of time might fly through a more complex landscape, but it still flies straight. time at the edge of the onion. While causality holds firm, time itself might not be so simple. Einstein's theories taught us that time is malleable. It can slow down in a strong gravitational field, a proven effect called time dilation. Brane cosmology suggests this could be even more pronounced. If our brane is rippling or interacting with another, some models suggest time could warp or stretch in ways beyond what standard relativity predicts. A contracting fourth spatial dimension could even make our three dimensions appear smoother and more uniform. This isn't time travel, but it hints that the flow of time might not be the same everywhere across our cosmic membrane. The cosmic screw thread, a new kind of geometry. The theories of curled-up dimensions and large branes aren't the only possibilities. A more speculative idea, from a team including physicist Richard Pinsick, suggests the strangeness is built into the geometry of spacetime itself, involving complex seven-dimensional structures called G2 manifolds. In this model, spacetime has a kind of built-in twist, or torsion, like the threads of a screw. This twisted geometry has a profound consequence. Particles might get their mass not from a Higgs field, but by interacting with the twists in spacetime. Mass emerges from the geometry itself. This theory is still in its early stages, but it proposes a potential way to test it by searching for a new particle, dubbed the torstone, which would be evidence that mass is a consequence of a fundamentally twisted, higher-dimensional geometry. The onion unfurls, explaining the expanding universe. This brings us to the greatest cosmological puzzle of all: dark energy. In the late 1990s, astronomers discovered the expansion of the universe is speeding up. This phenomenon accounts for roughly 68% of our universe, and we have no idea what's causing it. Extra dimensions offer some compelling ideas. In the brane world scenario, dark energy might be the energy of the bulk itself. One model, known as the ekpyrotic or cyclic universe, proposes that our universe is created by the collision of two parallel branes. The force pushing them apart after they bounce would look exactly like dark energy from our perspective. While this is an intriguing idea, recent data from surveys like DAISY have shown some tension with models of evolving dark energy, favoring the standard model for now, though not perfectly. The G2 manifold theory with its twisted geometry also offers an explanation. In that model, the complex geometry of the seven-dimensional spacetime itself naturally leads to cosmic acceleration. The expansion isn't being driven by something in space. It is a property of the twisted space itself. Finally, there's the holographic principle. It suggests our entire four-dimensional spacetime might be a holographic projection of information stored on a distant, two-dimensional surface. The expansion we observe could be a manifestation of this projection's geometry. Whether it's the force between branes, the inherent twist of spacetime, or the unfolding of a cosmic hologram, these theories all point to a stunning conclusion. The biggest mystery in our universe might only be solvable by looking outside it, into the hidden layers of the cosmic onion. We've been on a wild journey. We started with our familiar universe, haunted by a bizarrely weak gravitational force. This pushed us to a radical new idea: that particles are tiny, vibrating strings. This theory united gravity with the other forces but demanded our universe have 6 extra, hidden spatial dimensions. We explored how they could be curled up, or how we could be stuck on a brane, which would explain gravity's weakness and hint at a multiverse of parallel worlds. We plunged deeper still, finding that even in a world with extra dimensions, causality likely holds firm, and encountered newer, more speculative ideas, like a twisted geometry that could generate mass and cosmic expansion from its own structure. Are any of these ideas true? We don't know yet. String theory, for all its mathematical beauty, has been criticized for a lack of testable predictions and slow progress on its core problems. Experiments at the Large Hadron Collider have been searching for years for signs of extra dimensions, like microscopic black holes or energy vanishing into the bulk. So far, these searches have come up empty, though every null result helps scientists refine their theories. The High Luminosity LHC, set to begin operations in 2026, will collect 10 times more data, offering a much deeper probe. We are living in a remarkable time, peeling back layer after layer of the cosmic onion, only to find a world more complex and mysterious than the last. We may be trapped, but we're trapped in a structure of unimaginable grandeur. The quest to understand it is the greatest adventure of the human intellect. So next time you look up at the night sky, remember what you've learned. You might not be looking out into the abyss. You might be looking deeper into the onion. Trapped, perhaps, but part of a reality more magnificent, intricate, and mysterious than we could have ever imagined. Why scientists say the universe is too small. You've always been told the universe is impossibly vast. That you're a tiny speck floating in an endless ocean of galaxies, separated by distances your mind can't really process. It's a story of scale, of grandeur, of infinite space. But what if all of this, everything we see, everything we've ever measured, is just a tiny fraction of what's really out there? What if some of the most brilliant scientific minds are telling us that the universe we can see is, in a very specific way, too small? Now, this isn't a riddle. It's a conclusion that's been forced on us by the strange and beautiful mathematics that describes reality. It suggests our entire existence is a sliver of a much grander, and much larger, cosmic structure. To understand how, we don't need to travel to the edge of space. We just need to change how we look at it. Let's do a thought experiment. Imagine a universe called Flatland. It's completely flat, like an infinite sheet of paper. Its inhabitants are 2D-shaped circles, squares, and triangles. They can move left and right, forward and back, but the concepts of up or down are completely alien. Those directions literally don't exist in their world. Now, imagine you, a three-dimensional being, decide to pay a visit. You float above their flat world, totally invisible. If you try to speak, your voice seems to come from inside their own bodies, a disembodied sound from nowhere. To reveal yourself, you slowly lower your finger through their plane. What do they see? Not a finger. They see a single point appear out of thin air. As you lower your finger, that point expands into a small circle, which grows, changes shape, and then shrinks back to a point before vanishing. To a flatlander, this would be an inexplicable, terrifying miracle. They can't perceive your 3D finger. They can only see the 2D slice of it passing through their reality. This story, dreamed up over a century ago, is more than a clever parlor trick. It's the best analogy we have for one of the most profound ideas in all of physics. What if we are the Flatlanders? What if our entire three-dimensional universe is just a slice of a higher dimensional reality we can't perceive? It sounds like science fiction, but this idea comes from science's most ambitious quest: the search for a single theory that explains everything. And that quest has led physicists to a startling conclusion. For the laws of nature to finally make sense, the universe needs more dimensions than the three we can see. The problem: a tale of two universes. Modern physics is built on two colossal pillars. They are two of the most successful theories ever conceived, tested and confirmed to an absurd degree of accuracy. The problem is, where they ought to overlap, they violently disagree. They describe two incompatible realities, and this conflict is the biggest crisis in physics today. The first pillar is Albert Einstein's general theory of relativity. This is the theory of the very big. It describes the universe on the grandest scales: planets, stars, and galaxies. Einstein reimagined gravity not as a force, but as mass and energy warping the fabric of spacetime. The classic summary is that matter tells spacetime how to curve, and curved spacetime tells matter how to move. It's a beautiful, elegant theory of a smooth, predictable cosmos. Think of spacetime as a river. Heavy objects like stars or bowling balls dropped in, creating curves that guide smaller objects, like marbles, that roll nearby. This theory is solid. It's been proven by everything from GPS satellites to the bending of starlight and the detection of gravitational waves from colliding black holes. The second pillar is quantum mechanics. This is the theory of the very small. It governs the bizarre, chaotic world of atoms and subatomic particles. Unlike the smooth river of relativity, the quantum world is all about probabilities and uncertainties. Particles don't have a definite location until you look. They exist in a cloud of possibilities. They can be in multiple places at once. They can pop in and out of existence. It's a world built not on smooth curves, but on chunky, discrete packets of energy called quanta. This theory is the reason our digital world works. It's behind transistors, lasers, and computers. Its predictions are the most precisely confirmed in the history of science. For most things, this great divorce isn't an issue. Relativity handles the big stuff, quantum mechanics handles the small stuff. They stay in their own lanes. But there are places in the universe where this border breaks down, where the very big becomes the very small. I'm talking about two specific places: the moment of the Big Bang and the heart of a black hole. At the center of a black hole, a massive star collapses into a point of infinite density, a singularity. Here, you have immense gravity, relativity's turf, crammed into an infinitesimally small space, quantum mechanics turf. When physicists try to use both theories at once to describe what's happening, the math breaks. The equations spit out gibberish, like infinities. It's as if the two languages of physics are screaming at each other. One theory describes a smooth, continuous reality. The other describes a chunky, probabilistic one. They can't both be the whole story. This tells us our understanding is fundamentally incomplete. For nearly a century, the holy grail of physics has been to unite these two theories to find a theory of everything. And the most promising, most famous, and most controversial candidate is called string theory. It's a theory that solves the conflict, but it comes at a staggering price. We have to give up our most basic idea of the world we live in. The solution? A universe made of music. To see how string theory tries to heal this rift, you have to throw out your mental picture of a particle. Forget the idea that the building blocks of reality are tiny, point-like dots. Instead, string theory says that if you could zoom in on an electron or a quark, past what any instrument can see, you wouldn't find a point. You'd find a tiny, one-dimensional loop of vibrating energy. A string. That's the core claim. Everything in the universe, from the light hitting your screen to the atoms in your body, is made of these tiny, identical, vibrating strings. So, if everything is made of the same stuff, why do we have such a rich variety of particles? How do we get electrons, photons, and quarks? The answer is in the music of the strings. Just like a guitar string, these fundamental strings can vibrate in different ways. Each different vibrational pattern, or note, shows up as a different particle. A string vibrating one way looks like an electron. A different pattern makes it a photon. Another pattern, a quark. In this view, the universe isn't a collection of ingredients, it's a cosmic symphony. The laws of physics are the rules of harmony, the particles are the notes, and everything we see is the grand composition. And this simple, powerful idea has a profound consequence. One of the vibrational modes that naturally pops out of the math corresponds to a particle with zero mass that carries the force of gravity. This hypothetical particle, the graviton, is exactly what quantum mechanics predicted should exist. This is where the magic happens. By replacing dimensionless points with tiny strings, the theory smooths out the clash between general relativity and quantum mechanics. The problem with infinities at singularities arose from treating particles as infinitely small points. By smearing that point out into a string, the math suddenly behaves. The infinities disappear. The equations work. For the first time, gravity and the quantum world can be described by the same set of rules. String theory seems to unify the world of the very big and the very small. It's a framework that could be a theory of everything. It sounds perfect. Almost too perfect. Because as physicists dug into the math, they hit a bizarre, non-negotiable condition. A glitch in the system. The beautiful equations only worked, they were only mathematically consistent if the universe wasn't limited to 3 spatial dimensions. The implication. Why the universe is too small. This is the moment where reality starts to feel a bit strange. Scientists working on string theory weren't trying to find extra dimensions, they were just trying to make their theory work. But no matter what they did, they hit the same wall. The math kept producing nonsense, like negative probabilities, which are physically impossible. For all its beauty, the theory was broken. Then came the breakthrough. They discovered all these mathematical problems would magically cancel out and disappear if and only if the universe had more dimensions than the 3 of space we know and love. Let that sink in. The theory wasn't being tweaked to include extra dimensions for fun. The math itself demanded them. Early versions, called bosonic string theory, required a wild 26 dimensions. Later, more refined versions known as superstring theory brought that number down to a more modest 10 dimensions in total. That's 9 dimensions of space and 1 of time. This is the real meaning of the title. The universe we perceive, with its 3 dimensions of space length, width, and height is literally too small for the mathematics of string theory to function. Our 3D space just doesn't provide enough room for the strings to vibrate in all the ways needed to create the particles we see. To generate the complexity of our world, from electrons to photons to the graviton itself, the strings need more directions to wiggle in. Those directions are the extra spatial dimensions. So where are they? If we're living in a 9-dimensional spatial grid, why can't I just sidestep into the 4th dimension to avoid traffic? The proposed answer is as ingenious as it is strange. The extra 6 dimensions are hidden from us because they are unfathomably small. They're compactified or curled up on themselves at every single point in space. Think of a garden hose. From far away, it looks like a 1-dimensional line. You only need one number to describe a point on it, how far along it is. But as you get closer, you see that at every point along that line, there's also a 2nd dimension. A tiny circle you can move around, the circumference of the hose. From a distance, that 2nd dimension was invisible, too small to see. String theory suggests the 6 extra spatial dimensions are like the circle of the hose, but curled up on a scale far smaller than an atom, perhaps 1/100th of a billionth of an electron's diameter. They're hidden not because they're far away, but because they're everywhere, just too tiny to perceive. This means that at every single point in our universe, there exists a tiny, complex, 6-dimensional shape, often called a Calabi-Yau manifold. And the specific geometry of these curled-up dimensions isn't just a detail. The precise way they're folded determines the possible vibrations of the strings. And since the vibrations determine the particles and forces, the shape of these hidden dimensions dictates the very laws of physics for our universe. A slightly different shape would mean a universe with different physics, and perhaps one where life could never form. In fact, mathematicians estimate there could be a staggering number of possible shapes, perhaps 10 to the power of 500. That's a 1 followed by 500 zeros. This leads to an even grander, more speculative idea, the brane world scenario. In this picture, our entire 3-dimensional universe might be a brane, a membrane floating in a higher dimensional space called the bulk. We, and all the particles and forces of our world, except gravity, are stuck on this 3-brane, just like the Flatlanders were stuck on their 2D plane. In this scenario, it's possible other branes Other universes are floating parallel to our own, maybe just a millimeter away in a higher dimension, but completely invisible and inaccessible to us. The only force that isn't stuck to our brane, according to some versions of the theory, is gravity. This could explain why gravity seems so much weaker than the other forces. The reason a tiny magnet can beat the gravitational pull of the entire Earth might be because gravity's strength is being diluted as it leaks out into these extra dimensions. Okay, let's pause and breathe. We started with a huge crack in the foundations of physics. We found a potential solution: string theory that treats everything as music. But that solution only works if the universe we see is a shadow of a higher dimensional reality. If this is bending your mind a bit, you're in good company. This is some of the most challenging and exciting thinking in science. And if you enjoy wrestling with these huge ideas about reality, make sure you subscribe, because we're going to keep exploring the deepest questions there are. The search for the unseen. This is a fantastic story, but is it science? If these extra dimensions are real, they can't just be a mathematical trick. There must be tangible, observable consequences. Physicists are actively hunting for these fingerprints. One of the main hunting grounds is the Large Hadron Collider, or LHC, at CERN. The LHC smashes protons together at nearly the speed of light, hoping to shake something loose from these hidden dimensions. There are a few things they're looking for. One telltale sign would be a new set of particles. Theories with extra dimensions predict that our familiar particles should have heavier cousins, what physicists call Kaluza-Klein states. These would be heavier versions of normal particles, identical in every other way. A normal particle is a string vibrating only in our three large dimensions. A Kaluza-Klein particle would be a string that's also vibrating in one of the tiny, curled-up dimensions. That extra vibration would give it more energy, which we would detect as extra mass. Another strategy is to look for energy that just vanishes. Physicists at the LHC meticulously track all the particles that fly out of a collision. Energy in must equal energy out. But if extra dimensions are real, and gravity can travel through them, it might be possible for a collision to create a graviton that escapes, disappearing into the higher dimensional bulk. To our detectors, it would look like energy just vanished from the experiment. Finding a consistent pattern of such missing energy events would be powerful evidence. A third, more exotic possibility is creating microscopic black holes. In our 3D space, it takes immense energy to form a black hole. But if extra dimensions exist, gravity would get much stronger at very small distances. This means high-energy collisions at the LHC might briefly create tiny, transient black holes. They wouldn't be monsters. They'd be subatomic and would evaporate almost instantly in a puff of Hawking radiation. Their decay, however, would leave a spectacular and unique signature in the detectors. Beyond colliders, scientists are also looking for gravitational clues. Newton's famous inverse square law for gravity is a direct consequence of the force spreading out in 3 dimensions. If there are more dimensions for gravity to leak into, the force should drop off faster at very small distances. Extremely precise experiments are underway to measure gravity at sub-millimeter scales, looking for the slightest deviation from what Newton predicted. So far, the search has come up empty. No Kaluza-Klein particles, no confirmed missing energy, no micro-black holes. But this doesn't mean the theory is wrong. It could just mean the effects are more subtle, or require even higher energies to find than what we can currently produce. The hunt continues. The slice of reality. We started with a paradox. The most promising theory to explain our universe only works if that universe is dimensionally bigger than it appears. We went from the conflict between relativity and quantum mechanics to a solution in the form of vibrating strings, but that solution came with the profound implication that our reality is just a slice of a higher dimensional cosmos. These concepts compactified dimensions, our universe as a brane, are at the absolute frontier of knowledge. String theory itself isn't yet complete or proven. It's a work in progress. The fact that there are potentially 10 to the power of 500 ways for the extra dimensions to be shaped is a massive challenge in itself, often called the landscape problem. But whether or not string theory is the final theory of everything, it has fundamentally changed how we think about reality. It has given us a mathematical reason to question the very dimensionality of our world. It suggests the limits of our perception might be just that, our limits, not the limits of reality itself. We are like the inhabitants of Flatland. A 3D object passing through their 2D world seemed like an impossible, magical event. Perhaps the deep mysteries of our own universe, the bizarre rules of quantum mechanics, the nature of dark matter and dark energy aren't problems to be solved within our 3 dimensions. They might be the observable traces of a higher dimensional physics, phenomena that seem strange simply because we can't see the full picture. The idea that the universe is too small is ultimately a statement of humility. It's the recognition that what we experience as all of existence might be just one cross-section of a much larger, more complex reality. We may be living our entire lives on a single page of an infinite book, aware only of the words written there, oblivious to the vast story in the pages before and after. The search for what lies beyond our page is the ultimate adventure of science. And it forces us to wonder, what other truths about the cosmos are hiding in plain sight, just one dimension away?